There's a clock running right now that you can't see, can't hear, and never notice. It doesn't tick in seconds or minutes. It ticks in millennia, and for the past 1,000,000 years, this clock has been the single most powerful force shaping our planet, controlling whether ice sheets cover half the continents or melt into the oceans, deciding whether sea levels drop 400 feet or rise to drown coastlines, determining whether your city sits under a mile of ice or basks in temperate sun. The wild part, it's not in Earth's core, not in the oceans, not in the atmosphere, it's in the sky. Tiny wobbles in how Earth moves through space changes. So subtle you'd need 20,000 years to measure them, have been flipping climate between ice age and paradise on a schedule so precise you could set your watch to it. If your watch ran for 100,000 years, a Serbian mathematician figured this out in the 1920s with nothing but pencil and paper. Nobody believed him. Then we drilled into Antarctic ice, pulled up 800,000 years of frozen history, and found the pattern locked inside. He was right. For 1,000,000 years, this cosmic clock controlled everything. The ice came when it said come. The ice left when it said go. Then, 200 years ago, humans did something that should be impossible. We stopped the clock. And now, we have no idea what happens next. This is the story of the Ice Age machine and what it means that we just broke it. Welcome to episode 3. Close your eyes. Imagine standing in a valley in what is now central France. It is 20,000 years ago. You are at the height of the last glacial maximum, the coldest moment Earth has known in 100,000 years. To the north, where the horizon meets the sky, there is a white line. Ice. Not the ice of a winter storm, but a wall of frozen time, kilometers thick, stretching east and west as far as anyone has ever walked. The air burns to breathe. The valley is tundra-low scrub, mosses clinging to stone, the occasional dwarf birch twisted by wind. A small band huddles near a fire. They hunt reindeer, carve bone tools, tell stories their grandparents told them. This is the only world they've ever known cold and sparse, unyielding. Now imagine standing in the exact same valley, same latitude, same bedrock beneath your feet. But this time it is 120,000 years earlier, the Eemian, the last time Earth was this warm. The ice is gone, not retreating gone. Forests stretch north into lands that are tundra in your other vision. The air is thick with summer warmth, humidity clinging to skin, and if you listen carefully, past the rustle of oak and birch leaves, you might hear something impossible, the low grunt of a hippopotamus wallowing in what will one day be the Thames River. Elephants, not mammoths, but straight-tusked elephants with long, curving ivory brows in clearings. The sea laps at coastlines 6 to 9 meters higher than the ones you know. This world is not just warmer, it is fundamentally different. Same place. Same rock, same sky overhead, the same stars wheeling through their ancient patterns. 2 completely different Earths. What changed? Not the sun it burns with the same steady light, the same nuclear furnace it is tended for billions of years. Not the continents they've barely drifted a hand's breadth in the geologic blink between these moments. Not some asteroid strike or volcanic cataclysm. The answer is not beneath your feet. It is above you. In the slow, patient mathematics of Earth's motion through space, Earth wobbles, Earth tilts, Earth stretches its orbit like a drawn breath and then relaxes. Change is so subtle you'd never notice in 100 human lifetimes, a degree of tilt gained or lost over 40,000 years. a wobble that takes 26 millennia to complete one lazy circle, an orbit that shifts from nearly round to slightly egg-shaped and back again over 100,000 years. Invisible changes, astronomical changes, but profound enough to bury continents in ice, profound enough to melt them bare. For millions of years, Earth has cycled between ice ages and warm periods, not randomly, but in rhythm. There is a pattern here, a climate engine humming beneath the surface of time. The engine runs on 3 overlapping cycles, 3 slow dances Earth performs as it spins and orbits. A Serbian mathematician named Milankovitch figured this out in the 1920s, hunched over calculations in wartime Budapest, working everything by hand: the wobble, the tilt, the orbital stretch. He calculated how much sunlight reaches Earth's surface, specifically the high northern latitudes where ice sheets are born going back 600,000 years. His predictions were met with skepticism for decades. Too subtle, critics said. Changes too small to matter. Then, in the 1970s, scientists drilled into the ocean floor and pulled up cores of ancient mud. They drilled into Antarctic ice and extracted cylinders of frozen time. And in those cores, in the chemistry of tiny shells, in the trapped bubbles of ancient air, they found Milankovitch's rhythm, beating like a clock. 8 times in the past 800,000 years, ice has advanced and retreated. 8 glacial cycles, each one a slow descent into cold, followed by a rapid thaw into warmth. The pattern is clear now. Earth spends most of its time cold. For roughly 80 to 90 of the last million years, ice sheets have covered much of North America and Europe and Asia. Warm periods, interglacials, scientists call them, are the exception, not the rule. Brief interludes of mercy between long stretches of ice. You are living in one of those interludes. The Holocene, our current warm period, began only 11,700 years ago when the last great ice sheets finally gave up their grip on the northern lands. It is the warm pause inside which all of recorded human history has unfolded agriculture and cities and writing. Every empire that has risen and fallen. Every child ever born into what we think of as normal climate. But on the deep time scale that ice ages run on, the Holocene is an anomaly, a parenthesis, a breath between frozen ages and before our Holocene. The Eemian, that last warm world with its hippos in England, lasted about 15,000 years before the cold returned. Even warmer than today by a degree or two, with seas lapping 6 to 9 meters higher up the shores. Then the rhythm turned. Summer sunlight at high northern latitudes declined just enough, and snow that fell one winter didn't fully melt the next summer. Year after year, the snow accumulated, ice was born, and for the next 100,000 years, Earth descended back into cold. The ice will return, not in our lifetimes, not in 1,000 years. But the orbital clock is still ticking, and unless something fundamental changes, unless something breaks the ancient rhythm, the ice is patient. It remembers how to grow. Tonight, we are going to watch that clock. We will see Earth from outside, spinning and wobbling and tracing its path through space across thousands of years. We will watch how tiny changes in sunlight, a few percentage points of difference in summer radiation, reaching the Arctic trigger the growth of ice sheets kilometers thick. We will follow the pattern back hundreds of thousands of years through 8 glacial cycles preserved in ice and mud and stone. we will see why warm periods like ours are rare and precious, why they end, and where we are in the cycle now, and we will glimpse what all of this meant for the humans and near humans who lived inside this vast machine for hundreds of millennia, adapting to rhythms they could never see, but which shaped every aspect of their existence. This is the story of a climate engine powered by invisible astronomical gears. A clockwork universe that has been turning for millions of years, indifferent to the beings caught in its rhythm. The cycles are slower than empires, slower than species. They've been turning since long before humans walked upright, and they'll keep turning long after we are gone. You can drift if you need to. These rhythms operate on timescales that dwarf civilizations. The orbital machinery will still be humming when you wake, but for now, let us watch the dance. Let us see how the heavens move the ice. Step outside time with me for a moment. You are floating in the absolute stillness of space, far enough from Earth to see it whole a blue marble spinning against the black, the white swirl of clouds, the dark continents edged in the gleam of oceans. You are watching from a distance where years pass like seconds. One orbit around the sun takes one heartbeat. Seasons flicker across the face of the planet white, expanding from the poles in winter, green surging north in summer, so fast they blur into a breathing rhythm. You watch for what feels like minutes, but is actually millennia, and slowly you begin to notice something strange. 3 different movements, all happening at once, each so gradual that a human lifetime would never catch them. But from here, with time compressed, they are visible. First Earth's path around the sun is not quite a circle. It is an ellipse slightly stretched, like someone pulled a rubber band taut at opposite ends. And that ellipse is breathing. Over the course of what looks like 100,000 heartbeats, 100,000 orbits, 100,000 years, the path swells from nearly circular to noticeably egg-shaped, then relaxes back again. A slow pulse. Second, the planet itself is tilted as it spins. Its axis, the invisible line running from North Pole to South Pole, leans like a top that has been nudged off balance. Currently, it tilts at 23.4 degrees from vertical, but the angle is changing, barely perceptible even at this compressed time scale, but there the tilt slowly increasing, degree by patient degree, then decreasing again. The cycle takes 41,000 years. Right now, Earth is tilted about halfway between its extremes, and the tilt is very slowly decreasing. In 10,000 years, it will reach its minimum 22.1 degrees, then begin tilting more steeply again toward 24.5 degrees. A nod. A long, slow nod lasting tens of millennia. And third, most subtle of all the direction the axis points, is changing. Right now, if you followed Earth's North Pole out into space, it would point almost exactly at Polaris, the North Star. But the axis is wobbling, tracing a slow circle against the background of stars, like a spinning top winding down. 13,000 years ago, it pointed at Vega. 13,000 years from now, it will point at Vega again. The wobble takes 26,000 years to complete one full circle. 3 dances. 3 cycles overlapping and interfering, combining. From here, watching centuries pass in seconds, you can see what no human eye has ever witnessed. Earth's motion through space is not a simple, perfect loop. It is a complex choreography wobbling and tilting stretching its orbit all at once. Each movement subtle, each barely noticeable year to year, generation to generation, millennium to millennium. But when you speed time up enough, when you watch 100,000 years pass, in a few minutes the patterns emerge. The rhythms become visible, and you begin to understand that these tiny astronomical shifts, these invisible variations in Earth's dance through the void, are the conductors of a climate symphony that has been playing for millions of years. Down on the surface, at the northern latitudes where land masses concentrate and ice can grow, summer sunlight strengthens and weakens in response to these orbital movements, not by much, a few percent here, a few watts per square meter there, but enough, just enough. When the dances align in certain ways, when the wobble and the tilt and the orbital stretch synchronize into particular configurations, summer sunlight at high northern latitudes declines. Snow that falls in winter doesn't fully melt the next summer. Year after year it accumulates, compacts, becomes ice, and the ice begins to spread. Other times, other alignments, the opposite occurs. Summer sunlight intensifies at those critical northern lands. Ice melts faster than it can grow. The great sheets retreat, and the earth warms into a brief interglacial, a parenthesis of warmth between long ages of cold. 3 movements, 3 cycles. Together, they are the invisible clock that has been ticking in the background of Earth's climate for nearly 1 million years, pacing the advance and retreat of ice with mechanical regularity. Tonight we are going to watch each dance separately. We will see how they work, why they matter, and what they do to the planet beneath them. Then we will watch them combine the real magic, where 3 simple cycles weave together into the complex pattern that drives ice ages. The astronomy is about to become intimate, the orbital mechanics visual, the mathematics of celestial motion comprehensible, because this is not just about planets and orbits. It is about the world those orbits created, the world humans evolved in, adapted to, and ultimately learned to read. Let us begin with the first dance, the stretching orbit. Picture a circle. Perfect and round, every point on its edge exactly the same distance from the center. Now stretch it. Not violently, just a gentle pull at opposite sides, elongating it slightly into an egg shape. The stretched circle is now an ellipse. It still closes on itself, still loops, but one axis is longer than the other. This is eccentricity, how elliptical an orbit is, measured as the departure from a perfect circle. Earth's orbit around the Sun is always an ellipse, never a perfect circle. But the degree of stretch, the eccentricity, changes over time, oscillating between nearly circular when the orbit is almost round, with an eccentricity close to 0.3 and moderately elliptical when the stretch is more pronounced, with eccentricity reaching about 0.58. Currently, Earth's eccentricity is quite low, about 167. The orbit is nearly circular, which means Earth's distance from the Sun stays relatively constant throughout the year. At its closest point, perihelion, currently in early January, Earth is about 147 million kilometers from the Sun. At its farthest point, aphelion, currently in early July, it is about 152 million kilometers away. A difference of about 3 noticeable if you are measuring with precision instruments, but small enough that it barely affects the total amount of sunlight Earth receives. But this hasn't always been the case. and it will not always be the case. The eccentricity cycles, it oscillates from low to high and back again on multiple overlapping timescales. The dominant cycle is about 100,000 years, though there are also longer rhythms at roughly 400,000 years and shorter ones around 95,000 and 125,000 years. What drives these changes? The gravitational tugs of the other planets, primarily Jupiter and Saturn. These giant worlds, with their enormous masses, pull on Earth as it orbits, and those pulls slowly reshape the orbit's geometry over deep time. It is like children on swings pulling at each other, small tugs accumulating into noticeable shifts. Imagine watching this from space again, but now focused only on the shape of Earth's orbit. Over the course of 100,000 years, you'd see the ellipse gradually stretch, becoming more eccentric. Earth's distance from the Sun would vary more dramatically through the year, closer at perihelion, farther at aphelion. Then, and slowly, the ellipse would relax back toward circularity. Closer and farther would converge, and the orbit would become more uniform. Then the cycle would begin again, stretch and relax and stretch and relax, like a drawn breath and an exhaled one, repeated over geological epochs. Here's a human scale thought to anchor this A-band of people living in what is now southern France 50,000 years ago would have experienced an orbit only slightly different from ours. Over the span of their lives, their children's lives, their grandchildren's lives 10 and 20, 100 generations, the orbit would have looked essentially identical. They would not have noticed any change. But if you could time-lapse those 100 generations, then keep going for another 1,000 generations, you'd eventually see the orbital ellipse shift measurably. By 10,000 years from their time, the eccentricity would be slightly different. By 50,000 years, noticeably so. Effects too slow to perceive, but real. Written not in human memory, but in the geometry of Earth's path through space. So, what does this orbital stretching actually do to climate? Here's the counterintuitive part: not much. Not directly, anyway. When Earth's orbit is more elliptical, and yes, the distance from the Sun varies more through the year, but the total amount of sunlight Earth receives annually integrated over the whole year changes by only about 0.2. That is tiny. Barely a ripple. Not nearly enough on its own to trigger the growth or collapse of continent-spanning ice sheets. And yet, look at the climate record, going back 1 million years, the record extracted from ice cores and ocean sediments, which we will explore in the next chapter, and you will see a dominant pattern: glacial cycles recurring roughly every 100,000 years, the same period as the eccentricity cycle. The match is too close to be coincidence. Somehow, this weakest of the 3 orbital cycles has come to dominate the rhythm of ice ages. This is the 100,000-year problem, one of the great puzzles in climate science. How can the weakest forcing the one that changes total sunlight the least set the pace for the strongest climate response? The answer, as we will see later, is that eccentricity doesn't work alone. It acts as a pacemaker, a metronome that modulates the strength of the other cycles. Specifically, it amplifies and dampens the effect of precession, the third dance we will discuss shortly. When the orbit is more elliptical, precession matters more. When the orbit is nearly circular, precession's influence weakens. Eccentricity doesn't drive ice ages by itself, it controls how powerfully the other cycles can drive them. Think of it as a volume knob. Eccentricity sets the volume on Precession's signal. Sometimes the volume is high and Precession's influence on climate is strong. Sometimes the volume is low and Precession barely registers. The 100,000-year eccentricity cycle thus becomes the tempo underlying everything else, even though its direct effect is weak. But we are getting ahead of ourselves. To understand how this works, we need to meet the second dance. Stand up for a moment. Tilt your head to one side, not all the way to your shoulder, just part way. Maybe 15 or 20 degrees. That is roughly how Earth's axis is tilted relative to its orbit around the Sun. Earth spins like a top, rotating once every 24 hours, but the axis it spins on the invisible line from North Pole to South Pole is not perpendicular to the plane of its orbit. It is tilted. Currently, that tilt is about 23.4 degrees. This tilt is why we have seasons. In June, the northern hemisphere tilts toward the sun. Sunlight strikes the northern lands more directly, stays in the sky longer, and delivers more energy per square meter. Summer. Meanwhile, the southern hemisphere tilts away, receiving less direct sunlight. Winter. 6 months later, in December, the geometry reverses. The northern hemisphere tilts away winter, and the southern hemisphere tilts toward the sun's summer. If Earth's axis were not tilted, if it stood perfectly upright relative to its orbital plane, there would be no seasons. The sun would trace the same path across the sky every single day. The equator would be warm year-round, the poles cold year-round, and temperate latitudes would stay temperate forever. Life would be simpler. Also, and probably, much less interesting. But here's the key: the tilt is not fixed. It changes. Slowly. Over a cycle of about 41,000 years, Earth's obliquity varies between 22.1 degrees and 24.5 degrees. We are currently at 23.4 degrees, a bit less than halfway between the extremes, and the tilt is very gradually decreasing. In roughly 10,000 years, it will bottom out at 22.1 degrees. Then it will begin increasing again, reaching 24.5 degrees some 20,000 years after that, before cycling back down. Like the eccentricity cycle, this is driven by gravitational interactions with other bodies, primarily the Sun and the Moon pulling on Earth's equatorial bulge. And like eccentricity, the change is imperceptible on human timescales. No one alive 41,000 years ago noticed the tilt reaching its maximum. No one will notice it reaching its minimum 10,000 years from now. But the effect, accumulated over millennia, is profound. Here's why obliquity matters so much for ice. More tilt means stronger seasons. When Earth's axis is tilted at 24.5 degrees, its maximum, the difference between summer and winter, becomes more extreme. In the northern hemisphere, summers get hotter because the sun climbs higher in the sky and stays there longer. Winters get colder because the sun barely clears the horizon. High latitudes, and especially, feel this intensification. The Arctic gets more direct summer sunlight than it does at lower tilts. During peak summer at maximum obliquity, the sun can shine directly down on regions very close to the North Pole. Less tilt means weaker, milder seasons. When the axis is at its minimum 22.1 degrees, the contrast between summer and winter softens. Summers are cooler. Winters are warmer, relatively speaking. High latitudes receive less summer sun, and the poles never see the sun directly overhead even in midsummer. Now, here's the crucial insight that Milankovitch himself emphasized for ice sheets. What matters most is summer, not winter. The Arctic is cold enough for snow in winter no matter what the tilt is. Winter cold is not the limiting factor for ice growth. What determines whether snow accumulates into an ice sheet is whether summer is hot enough to melt it. Cool summers allow ice to grow. If summer at high northern latitudes is not intense enough, if the sun doesn't climb high enough, doesn't linger long enough, doesn't deliver enough energy to melt the snow that fell the previous winter, then that snow persists. It compacts under its own weight. Next winter, more snow falls on top. Next summer and again, not quite enough warmth to melt it all. Year after year, layer after layer, snow becomes firn, becomes ice. Over thousands of years, this accumulation becomes a glacier. Over tens of thousands of years, a continental ice sheet. Warm summers prevent ice from growing or cause existing ice to shrink. If summer at high latitudes is intense, if the sun beats down strongly for long hours, then the winter's snow melts completely. No accumulation. No ice growth. Existing ice sheets, if any, begin to waste away at their edges, their melt exceeding their growth. Obliquity controls this balance. At high obliquity steep tilt, high latitudes get more summer sun. Snow melts, ice retreats. The climate favors interglacial's warm periods. At low obliquity shallow tilt, high latitudes get less summer sun, snow accumulates. Ice advances. The climate favors glacial's cold periods. The effect is symmetric between hemispheres when obliquity changes. Both the north and south experience the same shift in seasonal intensity. But because most of Earth's landmass, and thus most of the potential ice sheet real estate, is in the northern hemisphere, that is where the action happens. The great ice sheets that have waxed and waned over the past million years grew primarily in three regions: North America, the Laurentide ice sheet, Northern Europe, the Fennoscandian ice sheet, and Northern Asia, all between about 45 degrees N and 75 degrees N latitude, all places where summer sun intensity, controlled by obliquity and the other cycles, determines ice's fate. And here's where Earth got lucky. Earth's obliquity is stable, confined to that 22.1 degrees to 24.5 degrees range because of the Moon. Our Moon is enormous relative to Earth, unusually large for a planetary satellite. Its gravitational pull, tugging on Earth's equatorial bulge, acts as a stabilizer. Without the Moon, calculations suggest Earth's tilt could vary chaotically over millions of years, swinging anywhere from nearly 0 degrees standing upright to as much as 85 degrees, tipped almost on its side. More recent simulations suggest the range might be somewhat less extreme, perhaps 20 to 25 degrees total variation, but still far more chaotic than the gentle 2.4 degree range we experience. For comparison, look at Mars. Mars has no large moon. Phobos and Deimos are tiny captured asteroids, gravitational weaklings. Without a stabilizer, Mars's obliquity varies wildly over timescales of millions of years, from as low as 0 degrees to as high as 60 degrees, perhaps more. When Mars is tilted steeply, its poles receive intense summer sunlight water ice sublimates from the polar caps and migrates toward the equator. When Mars tips back toward vertical, the poles freeze solid and the equatorial regions dry out. The result dramatic, chaotic climate shifts that have likely left geological scars across the Martian surface. Earth, by contrast, is blessed with a gentle, predictable 41,000-year wobble in its tilt. The moon keeps us from the chaos that Mars endures, and that stability, ironically, is what allows the Milankovitch cycles to work. If Earth's tilt varied unpredictably, if it lurched from 10 degrees to 70 degrees and back over short time scales, there would be no regular pattern to ice ages. Climate would be violently unstable. Complex life might never have had the steady platform it needed to evolve. Instead, we get a slow, rhythmic nod. 23 degrees, 24 degrees, 22 degrees, back to 23, over and over, like a metronome ticking in deep time. And that nod, combined with the other dances, creates the pattern. Spin a top on a table. Watch it for a few seconds. If it is slightly off balance, if it is not spinning perfectly upright, you will notice something: the axis itself wobbles. The top is spinning fast around its own axis, and yes, but that axis is also tracing a slow circle in the air. The tip of the axis draws a cone shape as it wobbles. This is precession. Earth does the same thing. As Earth spins on its tilted axis once every 24 hours, that axis is also wobbling, tracing a slow, lazy circle against the background of stars. The wobble is caused by the gravitational pulls of the sun and the moon on Earth's equatorial bulge. And it is slow. Excruciatingly slow. One complete wobble, one full circuit of that wobble cone takes about 25,700 years. Right now, Earth's North Pole points almost directly at Polaris, the North Star. That is why Polaris stays fixed in the northern sky while all the other stars appear to wheel around it. But 13,000 years ago, the North Pole pointed at Vega, a bright star in the constellation Lyra, and 13,000 years from now, it will point at Vega again. The axis is wobbling through the stars, patient and relentless. For naked eye stargazers in ancient civilizations, this wobble was discovered as the precession of the equinoxes, the slow shift in which constellation the sun appears in during the spring equinox. The ancient Greeks noticed it. They couldn't explain it, but they measured it. It is one of the subtlest motions in the heavens, detectable only by comparing observations separated by centuries. But here's the part that matters for climate. This wobble changes when in Earth's orbit the seasons occur. Currently, Earth reaches perihelion, its closest point to the Sun, in early January. That is Northern Hemisphere winter, Southern Hemisphere summer. So the Southern Hemisphere gets a slightly more intense summer because Earth is closer to the Sun, while the Northern Hemisphere gets a slightly less intense summer because Earth is farther from the Sun when it is tilted toward it 6 months later, at aphelion in early July. But 13,000 years ago, the geometry was flipped. Perihelion occurred in July Northern Hemisphere summer. The Northern Hemisphere was tilted toward the Sun, and Earth was at its closest approach. Double boost. Summer insolation at high northern latitudes was significantly stronger than it is today. Meanwhile, the Southern Hemisphere experienced its summer at aphelion, when Earth was farthest from the Sun. Weaker summer there. This is the essence of precession's climate effect. It determines which hemisphere gets more intense seasons and which gets milder ones. When one hemisphere's summer coincides with perihelion, that hemisphere experiences stronger seasonal contrast. The other hemisphere experiences weaker contrast. Then, over the course of 23,000 years, the climate precession period, which combines axial, precession with the precession of Earth's elliptical orbit itself, the pattern flips. The effect is most pronounced when Earth's orbit is highly eccentric. Here's where eccentricity and precession interact. If Earth's orbit is nearly circular, as it is now perihelion and aphelion, are almost the same distance from the Sun, the difference is only about 3, so it doesn't matter much when in the orbit summer occurs. The boost from being at perihelion during summer is tiny. But when the orbit is highly elliptical, when eccentricity is at its peak, perihelion and aphelion are significantly different distances. The difference can be as much as 6 or 7. Now it matters a lot whether summer happens at perihelion or aphelion. The contrast is strong eccentricity to noticeably affect how much energy high latitudes receive during the critical summer months. This is why eccentricity acts as a pacemaker. Precession cycles along happily every 23,000 years, flipping which hemisphere gets stronger summers. But when eccentricity is high, those flips have teeth they create real, substantial differences in solar forcing. When eccentricity is low, the flips are gentler, barely noticeable. The result a complex, beating pattern. Precession creates a 23,000-year rhythm. Eccentricity modulates that rhythm over 100,000 years, making it strong during some cycles and weak during others. Together, they produce a signal that waxes and wanes, pulses and fades, in a pattern far more intricate than either cycle alone. And it gets even more complex, because Obliquity, the 41,000-year tilt cycle, is operating simultaneously, adding its own voice to the chorus. When all three align, when high eccentricity coincides with precession putting northern summer at perihelion and low obliquity creating weak summers, the combined effect can tip the balance toward glaciation. When they align the opposite way, high obliquity, northern summer at perihelion, during high eccentricity, the ice melts. Let us watch what happens when these three dances combine. Imagine 3 musicians, each playing a different instrument with a different tempo. One plays a slow, deep drumbeat boom, boom, boom. 1 beat every 100,000 years. This is eccentricity, the 100,000-year pulse of the orbital stretch. Another plays a faster rhythm on a hand drum tap, 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 tap. 1 beat every 41,000 years. This is Obliquity, the tilt cycle. The third plays a quick, intricate melody on a flute trill, 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 trill. Notes every 19 to 23,000 years. This is Precession, the wobble. None of them is following the same sheet music. They are not coordinated. Each musician plays their own part, independent of the others. And yet, when you listen to all 3 at once, patterns emerge. Sometimes the beats are line drum, hand drum, and flute all hitting a note together. Those moments are powerful, reinforcing. Sometimes the rhythms oppose each other. The drum hits while the flute rests. The hand drum comes in offbeat. Those moments cancel out, create interference. This is how the Milankovitch cycles work. 3 overlapping rhythms, sometimes synchronizing, sometimes clashing. The result is not a simple, repeating pattern. It is a complex waveform and interference pattern that creates periods of strong forcing when the cycles align to reduce summer sunlight at high northern latitudes, and periods of weak forcing when they align to increase it, or when they cancel each other out. Scientists can calculate this combined effect precisely, using the known periods and amplitudes of each cycle, plugging in the mathematics of celestial mechanics. We can compute exactly how much sunlight has struck any given latitude at any given season going back millions of years. The key metric, the one Milankovitch himself focused on, is summer insolation at 65 degrees N. Why 65 degrees N? Because that is where the landmass is. That is where ice sheets form. Most of the northern hemisphere's land between the Arctic Circle and the temperate zones sits near this latitude: Scandinavia, northern Canada, Siberia. These are the nurseries of ice. And land matters because land heats and cools faster than ocean. An ice sheet needs solid ground to grow on. You cannot build a continental ice sheet in the middle of the ocean. So summer insolation at 65 degrees N becomes the master variable. When this value is high, when the combination of eccentricity and obliquity and precession delivers intense summer sunlight to the critical northern latitudes, ice melts. Interglacials begin. When it is low, when the cycles conspire to reduce summer sun, ice grows. Glacials begin. Plot this insolation value over time, and you get what's called an insolation curve, a wiggly line, showing the rise and fall of summer sun at 65 degrees N, going back hundreds of thousands, even millions of years. Now plot the Ice Age record next to it. The match is remarkable. Not perfect ice sheets do not respond instantaneously to changes in sunlight. And there are internal feedbacks in the climate system, which we will explore in later chapters, that complicate the relationship. But the correlation is strong enough to confirm Milankovitch's insight orbital forcing drives ice ages. The dominant periods visible in climate records: 100,000 years, 41,000 years, 23,000 years match the orbital cycles. When scientists use spectral analysis, a mathematical technique for extracting repeating patterns from noisy data on ice core and ocean sediment records, those three frequencies jump out like bell tones, proof that Earth's climate dances to the rhythm of its orbit. But here's the fascinating part, the part that reveals the system's complexity. The strength of these signals in climate records doesn't match the strength of the orbital forcing. Eccentricity, the weakest direct forcing, produces the strongest climate response over the past million years. The 100,000-year cycle dominates the ice age pattern, even though eccentricity barely changes total sunlight. Obliquity and precession, which have stronger direct effects on sunlight, show up clearly in the record, but do not dominate the way you'd expect. Why? Because the climate system is not a simple amplifier that just echoes whatever signal you feed it. It has its own dynamics, its own internal rhythms, its own preferences. Ice sheets have memory. They take thousands of years to grow and thousands to melt, and that inertia creates resonances, natural frequencies, at which the system likes to oscillate. The 100,000-year period, it turns out, matches the ice sheet's own preferred timescale for growth and collapse. So eccentricity, though weak, acts as a metronome that keeps the ice sheet synchronized at that period. This is what we mean when we say eccentricity is a pacemaker rather than a driver. It doesn't force the ice ages directly. It sets the tempo that the ice sheets follow. We will dig into these complexities, the feedbacks, the lags, the nonlinear responses in Chapter 3. For now, the key point is this: the three orbital cycles combine to create a pattern of varying solar forcing at high northern latitudes. And that pattern, filtered through the dynamics of ice sheets and amplified by feedbacks in the climate system, produces the ice age rhythm we see in the geological record, a rhythm that has persisted with remarkable regularity for nearly 1 million years. Why this matters for ice, let us bring this back to the ice itself, to the physical reality of snow accumulating and compacting, spreading, because all of this orbital geometry, all these wobbles and tilts and ellipses, matters only insofar as they affect one thing, whether snow that falls in winter melts in summer. That is the hinge. The Arctic is cold. Scandinavia in winter, northern Canada in winter, Siberia in winter, these places are cold enough for snow. Always have been, always will be, at least for the foreseeable future. Winter snowfall is not the limiting factor for ice sheet growth. Summer is the gatekeeper. If summer at these high latitudes is warm enough, if the sun climbs high enough in the sky, lingers long enough, delivers enough energy, then the snow that fell the previous winter melts. Water runs off into rivers, flows to the sea, evaporates back into the atmosphere. The landscape clears. No accumulation. The ice budget for that year is 0 or negative if there is existing ice to melt. But if summer is cool, if the sun stays low, if the days are shorter, if clouds block some of the incoming radiation, then not all the snow melts. Maybe most of it does, but a thin layer remains. 1 meter, 2 meters, scattered across the high valleys and plateaus. Come next winter, fresh snow falls on top of that remnant. Come next summer and again, not quite enough heat to melt it all. The remnant grows. Another meter, another 2. Year after year, the accumulated snow compacts under its own weight. Air gets squeezed out. Snow becomes firn-dense. Granular old snow, firn becomes ice. In the beginning, this is just a local phenomenon. A few valleys in Scandinavia holding year-round snow. A few highland plateaus in Canada where summer never quite clears the winter's burden. But ice doesn't just sit there. Once it is thick enough, a few hundred meters, it begins to flow outward under its own weight, spreading like a slow, frozen flood. The ice flows down from the highlands into the lowlands. It reaches the coast. It keeps going out onto the continental shelf. As long as summer remains cool enough that the ice's growth exceeds its melt, the ice sheet expands. And expanding ice creates feedback. The white surface reflects sunlight, cooling the region further, allowing even more ice to persist. A positive feedback loop. Over thousands of years, 10,000, 20,000, 40,000, the ice sheet grows from scattered mountain glaciers into a continent-spanning behemoth. At the last glacial maximum, 20,000 years ago, the Laurentide ice sheet covered all of Canada and much of the northern United States, in places more than 2 miles thick. The Fennoscandian ice sheet buried Scandinavia and reached across the North Sea into what is now Britain. And all of this, every cubic kilometre of that ice grew because summer was not hot enough to melt the winter's snow. Now reverse it. Deglaciation, the melting of ice sheets, can happen faster than glaciation. Why? Feedbacks work in reverse, but more powerfully. When ice starts to melt, it exposes dark ground or ocean beneath. Dark surfaces absorb sunlight instead of reflecting it. The region warms. More ice melts. More dark surface is exposed. The warming accelerates. Meanwhile, as ice thins at the edges, it flows faster, sending more ice toward lower, warmer latitudes where it melts even faster. And as we will see in later chapters, carbon dioxide released from the ocean during warming amplifies the process further. The result, ice sheets can collapse in 10 to 20,000 years much faster than the 60 to 80,000 years it took them to grow. This asymmetry, slow growth, fast collapse creates the sawtooth pattern visible in climate records. Glacial periods are long, drawn-out affairs with ice slowly accumulating. Interglacial periods arrive suddenly, relatively speaking, with ice melting in rapid bursts called terminations. The pattern repeats long freeze, quick thaw, long freeze, quick thaw, over and over. And the pacing of this rhythm, the trigger that determines when the slow freeze ends and the quick thaw begins. Summer sunlight at 65 degrees N, driven by the Milankovitch cycles. When the orbital configuration aligns to deliver strong summer sun to the high northern latitudes, when eccentricity is high, precession puts northern summer at perihelion, and obliquity tilts the north strongly toward the sun the ice cannot hold. Summer melt exceeds winter accumulation. The balance tips. Deglaciation begins, and when the configuration reverses, low summer sun, weak insolation, cool Arctic summers that cannot melt the snow ice begins its slow, patient advance once more. This is the machinery. This is how invisible astronomical cycles, operating on timescales of tens of thousands of years, translate into the physical reality of ice sheets kilometers thick, grinding across continents, reshaping landscapes, and transforming the entire planet's climate. 3 dances, 3 cycles. Together, they become the climate engine. So Earth dances 3 different dances, at once stretching its orbit, tilting its axis, wobbling like a top. Each dance, on its own, would barely affect climate. A fraction of a degree here, a few watts per square meter there. Subtle, gentle, forgettable. But together, when they align in certain ways, they become something far more powerful. They become the engine that drives ice ages, the invisible force that has buried into entire continents in ice, then melted them bare, over and over, for nearly 1 million years. To truly see this engine at work, though to confirm that these theoretical cycles actually match reality, we need evidence. We need to look into the frozen archives of Earth's past ancient ice, holding trapped air from 100,000 years ago, ocean mud recording the rise and fall of ice sheets through chemical signatures left by microscopic shells. We need to see the pattern, to read the rhythm written in ice and stone. That is where we turn next. The room is cold. Not quite Antarctica cold, you can breathe without your lungs aching, but cold enough that you can see your breath, cold enough that the exposed skin on your face tightens. The temperature is set to -20 Celsius, kept deliberately frigid to preserve what sits on the steel table before you, a cylinder of ice, roughly 10 centimeters in diameter, extracted from 2 miles beneath the surface of the Antarctic ice sheet. A scientist in thermal gear carefully positions a specialized saw. The ice is blue-white, translucent in places, clouded in others, and within it you can see something miraculous layers. Hundreds of them. Each represents 1 year's snowfall, compressed over millennia into this frozen archive. Some layers are darker summer snow, containing more dust. Some lighter winter snow, cleaner. They stack like the pages of a book, each one recording conditions when it fell. The saw bites in with a whisper. A thin wafer of ice, no thicker than a microscope slide, falls away. This particular section came from a depth of 2,400 meters. That corresponds, according to the careful dating work done, by counting layers and matching chemical markers, to ice that formed approximately 100,000 years ago, the Eemian interglacial, the last time Earth was as warm as it was in the pre-industrial Holocene. The scientist holds the wafer up to the light. Visible within the ice, if you look closely, are tiny bubbles. Each bubble is a trapped parcel of ancient atmosphere air that last touched the surface of Antarctica when mammoths roamed Siberia and Neanderthals lived in Europe. The chemical composition of that air, its ratio of carbon dioxide to oxygen, its methane content, its isotopic signature is about to be measured with exquisite precision. This ice is a time capsule, a climate library, and it is one of thousands of such sections extracted from the Antarctic interior, each revealing a piece of the planet's climatic past. Close your eyes now and imagine the work drilling down through ice that accumulates at a rate of just a few centimeters per year. Every meter of core represents hundreds, sometimes thousands of years. By the time you reach bedrock, 3 kilometers down, you've punched through ice that fell as snow 800,000 years ago. 800,000 years of Earth's climate, frozen, preserved, waiting to be read. This is how we know about the Ice Age cycles, not from theory alone, not from mathematical models of orbits. We know because the ice remembers, because the ocean floor remembers, because tiny shells of microscopic creatures buried in mud miles beneath the sea record in their chemistry the exact conditions of ancient oceans. Tonight we are going into those archives. We are going to see how scientists extract climate from ice and stone, how they date layers going back nearly 1 million years, and how the patterns they've uncovered match with stunning precision the orbital cycles we explored in the last chapter. We are going to watch Milankovitch's theory come alive in data. Picture a cylinder, 10 centimeters across, 3,000 meters long, one continuous piece of ice, extracted intact from the Antarctic ice sheet like pulling a straw of frozen atmosphere straight out of deep time. This is an ice core. The longest and most famous of these cores come from 2 places: Vostok Station in East Antarctica, where Russian and French scientists drilled to a depth of 3623 meters and recovered ice spanning 420,000 years, and Dome C, also in East Antarctica, where the European project for ice coring in Antarctica, EPICA, drilled even deeper 270 meters and reached ice 800,000 years old. 800,000 years. Think about that for a moment. When the snow that became the deepest ice at Dome C first fell, modern humans didn't exist. Homo erectus still walked the earth. The planet was in the grip of a glacial period we now call marine isotope stage 20. And all of it, every winter's snow, every summer's dust, every bubble of ancient air is still there, compressed into layers so thin they are measured in millimeters, stacked atop one another in perfect chronological order. How do ice cores work as climate archives? Start with the basics. Snow falls in Antarctica, layer upon layer, year after year. Because Antarctica is so cold and dry, the snow doesn't melt, it just accumulates. As new snow piles on top, the older snow beneath compresses under the weight. Air gets squeezed out. The snow becomes firn-dense, granular material partway between snow and ice. Eventually, under enough pressure, firn becomes glacial ice, solid and blue, ancient. But not all the air escapes. Some gets trapped in tiny bubbles as the firn compacts into ice. These bubbles are pockets of fossil atmosphere sealed off from the modern world, preserving the exact composition of air from the time the bubble closed. Scientists can extract these bubbles, analyze the gases inside, and directly measure atmospheric carbon dioxide and methane and other trace gases from hundreds of thousands of years ago. That is the first treasure in ice core's ancient atmosphere, captured in glass like prisons of ice. The second treasure is in the ice itself. Water molecules are not all identical. Most water is HO made from the common isotope of oxygen, oxygen-16, which has 8 protons and 8 neutrons, but about 1 in every 500 oxygen atoms is oxygen-18 with 2 extra neutrons, the heavier isotope. When water evaporates from the ocean, the lighter molecules containing O16 evaporate more easily. When water vapor condenses into rain or snow, the heavier molecules containing O18 condense more readily. This means that as moisture-laden air travels from the tropics toward the poles, it progressively loses its heavy oxygen through precipitation. By the time air reaches Antarctica and dumps its snow, that snow is severely depleted in O18. But here's the key: how depleted it is depends on temperature. In colder climates, the fractionation process is more extreme. More heavy oxygen rains out early in the air mass's journey. The snow that eventually falls in Antarctica is even more enriched in O16 than usual. In warmer climates, the process is less extreme, and the snow retains slightly more O18. Scientists measure this as a ratio 18 to O16, and that ratio acts as a thermometer. Lower ratios more O16 colder temperatures when the snow fell, higher ratios more O18 warmer temperatures. Each layer of ice and then carries a temperature's signature. By measuring the isotope ratios down the length of a core layer by layer, year by year, scientists can reconstruct temperature changes going back as far as the ice goes. And it is not just temperature. Ice cores also tell you about dust. During glacial periods, the world was drier, windier. More dust blew from exposed continental shelves and deserts. Antarctic ice from glacial times contains 10 to 25 times more dust than ice from interglacial periods. You can see this visually. Glacial ice looks cloudy, filled with fine particles. Interglacial ice is clearer. Volcanic eruptions, ash layers from major eruptions, get deposited in the ice and preserved. These serve as time markers if you can date the eruption independently. You can use it to calibrate the ice core's chronology. Snowfall rates. Thick layers mean heavy snowfall. Thin layers mean light snowfall. This correlates with temperature, warmer, more evaporation from ocean, more precipitation, and helps reconstruct past climate dynamics. Put it all together, and an ice core becomes a multi-proxy climate record. Temperature from oxygen isotopes, atmospheric composition from air bubbles, aridity from dust, volcanic activity from ash. Each core is a library, and scientists have learned to read it with extraordinary precision. The EPIC Dome C core at 800,000 years revealed something profound. Earth has cycled through roughly 8 complete glacial-interglacial oscillations during that span. 8 times the climate swung from deep cold to relative warmth. 8 times carbon dioxide levels rose and fell in near perfect synchrony with temperature. 8 times the ice advanced and retreated. Each cycle lasted approximately 100,000 years. The pattern is so regular it is almost mechanical, and when scientists compared these cycles to the calculations of summer insolation at 65 degrees and the predictions from Milankovitch's orbital theory, they found a match. Not perfect, not one-to-one, but close enough to confirm that orbital forcing drives the rhythm. But ice cores alone do not tell the whole story. They are limited to places where ice has survived Greenland and Antarctica, a few high mountain glaciers. To see the global picture, to understand how ice ages affected the entire planet, we need a different archive. We need the ocean floor. The deep ocean is dark, cold, still. 3 miles below the surface, no light penetrates. No currents disturb the sediment. And onto that sediment, and constantly and slowly, falls a gentle rain, the bodies of microscopic organisms that lived in the sunlit surface waters above. These organisms, plankton, mostly are so small you'd need a microscope to see an individual. But they are staggeringly numerous. Billions upon billions live and die in the ocean's upper layers. When they die, their shells sink down through the water column, slowly tumbling, eventually settling on the ocean floor like biological snowflakes. Over time, thousands of years, hundreds of thousands of years, these shells accumulate. The mud thickens, layer upon layer, each preserving a snapshot of ocean conditions at the time the organism was alive. This is the ocean's archive. And unlike ice cores, which are geographically limited, ocean sediment cores exist everywhere there is an ocean floor. They provide a global climate record going back not just hundreds of thousands of years, but tens of millions. The organisms whose shells matter most for climate reconstruction are called foraminifera forams for short. They are single-celled protists, amoeba-like creatures that build intricate shells of calcium carbonate. Different species of forams live in different water temperatures. Some thrive in tropical warmth, others in polar cold. When scientists drill a sediment core and find the shells of cold-loving forams in a region where warm-loving species dominate today, they know the ocean at that location was once much colder. But species composition is just the start. The real power of forams lies in their chemistry. Remember oxygen isotopes from ice cores. The same principle applies in the ocean, but in reverse. When ice sheets grow during glacials, they preferentially lock up the lighter oxygen isotope O16 on land. The ocean is left enriched in the heavier isotope O18. Forams build their calcium carbonate shells using oxygen from seawater, so their shells incorporate the ocean's isotopic signature. Shells formed during glacial periods have higher O18 ratios. Shells formed during interglacials, when ice sheets have melted and returned O16 to the ocean, have lower O18 ratios. Here's the beautiful part: this signal is global. It doesn't matter where the foram lived. A foram in the Pacific, a foram in the Atlantic, a foram off the coast of Antarctica all record the same global ice volume signal because ocean water mixes on timescales of about 1,000 years, fast enough that the isotopic composition of the entire ocean homogenizes between glacial-interglacial transitions. This means scientists can take sediment cores from dozens, even hundreds of sites around the world, measure the oxygen isotope ratios in foram shells, and construct a globally averaged record of ice volume over time. And that is exactly what they've done. In 2005, Lorraine Lisiecki and Maureen Ramo published what's known as the LR4 stack, a composite record of oxygen isotope measurements from 57 deep sea sediment cores distributed across the globe, spanning the past 5.3 million years. It is the most comprehensive picture we have of Earth's ice age history. The record shows glacial interglacial cycles going back millions of years. Before about 1 million years ago, the cycles occurred every 41,000 years, matching the Obliquity tilt cycle. After 1 million years ago, the rhythm shifts to 100,000-year cycles, matching the eccentricity period. This shift, called the mid-Pleistocene transition, is one of the great puzzles in paleoclimatology. Why did the climate system's response change? We will explore that in the next chapter. For now, the key point is the ocean sediment record reveals the pattern. It shows the rhythm, and it matches the orbital forcing. Scientists have even numbered the cycles. They are called marine isotope stages, or MIS for short. Imagine you are a climate scientist in the 1960s. You've just received oxygen isotope data from a deep sea core drilled somewhere in the Pacific. The data shows oscillations, peaks and troughs in the 018 ratio, indicating alternating glacials and interglacials. But how do you talk about them? How do you refer to specific warm or cold periods in a way that other scientists will understand? You need a numbering system. In 1955, Cesare Emiliani, one of the pioneers of paleoclimatology, proposed exactly that. He numbered the isotope peaks and troughs, working backward from the present. The current warm period, the Holocene, became stage 1. The last glacial period became stage 2. The previous interglacial, the Eemian, became stage 5. And so on, backward through time. The system that emerged from Emiliani's work and subsequent refinements is now standard across the field odd numbers interglacials warm periods. Low 018 values, less ice on land, higher sea levels. Even numbers glacials cold periods, high 018 values, more ice on land, lower sea levels. The numbering runs from the present Holocene all the way back to MIS 104 and beyond more than 6 million years ago, into the Pliocene. Here are the highlights of recent cycles, MIS 1 present to 11,700 years ago, the Holocene. Our current interglacial, stable and warm, the period in which human civilization arose. MIS 24 roughly 110,000 to 12,000 years ago, the last glacial period. Ice sheets covered Canada, northern Europe, parts of Siberia. Sea levels dropped 120 meters below present. The coldest point, MIS 2, the last glacial maximum, occurred around 20,000 years ago. MIS 5e approximately 130,000 to 115,000 years ago, the Eemian interglacial. The last time Earth was as warm as the pre-industrial Holocene. In fact, it was warmer. Global temperatures were 1-2 degrees Celsius higher than pre-industrial levels, and sea levels were 6-9 meters higher. Hippos lived in the Thames River Valley. Forests grew in parts of what is now the Sahara. MIS Fivia, favic oscillations within the last glacial cycle, briefer warm spells, interstadials, interrupting the descent into full glaciation. Not as warm as full interglacials, but warmer than the surrounding cold periods. These substages show that transitions between glacial and interglacial are not always smooth. The climate stutters and oscillates, swings back and forth, before settling into its new state. MIS 6 191,000 to 130,000 years ago, the penultimate glacial period. A deep freeze, comparable to the last glacial maximum. MIS 7 and 9, 11 earlier interglacials, each unique. MIS 11, around 400,000 years ago. was particularly interesting. It lasted much longer than most interglacials, possibly 30,000 years, and had orbital characteristics similar to our own. Some scientists consider it a potential analogue for how the Holocene might have evolved without human influence, and so on, backward through time. 17 major glacial interglacial cycles over the past 1.8 million years. 8 complete cycles in the past 800,000 years, the span covered by the EPIK ice core. Each cycle unique in its details, duration, peak warmth, the specifics of its orbital configuration, but all following the same basic pattern: slow descent into cold, rapid climb out into warmth. The sawtooth shape that emerges from the data is unmistakable. Ice cores and ocean cores do not just confirm each other, they complement each other. Ice cores provide high-resolution detail and direct atmospheric measurements. Ocean cores provide global coverage and extend much further back in time. Together, they give us a complete, cross-validated picture of Earth's climate history. And when you overlay that history with the predictions from Milankovitch cycles, when you plot summer insolation at 65 degrees N alongside the ice volume record, the match is striking. It is the early 1970s. Scientists have ocean sediment cores showing clear 100,000-year glacial cycles. They have Milankovich's calculations showing orbital variations on the same timescales. But do the two actually line up? In 1976, James Hayes, John Embry, and Nicholas Shackleton published a landmark paper in the journal Science Variations in the Earth's orbit pacemaker of the ice ages. They analyzed deep-sea cores from the southern Indian Ocean, carefully dating the Forum-based oxygen isotope record. Then they performed spectral analysis, a mathematical technique that identifies repeating patterns, periodicities in noisy data. Think of it like listening to a complex musical chord and teasing out the individual notes. What they found: 3 dominant frequencies in the climate record: a 100,000-year cycle, a 41,000-year cycle, a 23,000-year cycle, eccentricity, obliquity, precession. The orbital periods predicted by Milankovitch matched the climate periodicities observed in the data, not approximately, not loosely. They matched. This was confirmation, proof that orbital variations drive ice ages. Milankovitch had been right all along. But the match is not perfect. It is more subtle than a simple one-to-one correspondence. For instance, the 100,000-year cycle dominates the ice volume record over the past million years, even though eccentricity, the orbital parameter, with a 100,000-year period, has the weakest direct effect on sunlight. How can the weakest forcing produce the strongest response? And why did the climate system's preferred periodicity shift from 41,000 years before the mid-Pleistocene transition around 1 million years ago to 100,000 years after the transition? The orbital forcing didn't change. Earth's wobble and tilt and orbital eccentricity were doing the same things 1 million years ago that they are doing now. So why did the climate's response change? These are deep questions, and we will explore them in the next chapter when we dive into ice sheet dynamics, feedback loops, and the infamous 100,000-year problem. For now, the key point is this: the correlation is clear. Orbital forcing paces ice ages. The evidence from ice and ocean sediments confirms it beyond reasonable doubt. Let us look at the sawtooth pattern more closely. If you plot ice volume or temperature or oxygen isotope ratios, they all show the same basic shape over the past 800,000 years. You see a repeated motif slow descent into glaciation. Starting from an interglacial, temperatures gradually decline over 60,000 to 80,000 years. Ice sheets grow slowly, spreading across northern land masses. Sea levels drop as water is locked up in ice. The descent is bumpy. There are brief warm spells, temporary retreats, but the overall trend is toward cold. Prolonged glacial maximum. For thousands of years, the climate stays locked in deep cold. Ice sheets reach their maximum extent. Dust storms rage over exposed continental shelves. The world is dry and windy, harsh, rapid deglaciation. Then, suddenly on geological timescales, the ice melts. Over just 10,000 to 20,000 years, sometimes even faster ice sheets collapse, seas rise, temperatures spike. The transition from glacial to interglacial happens far more quickly than the transition into glaciation. Brief interglacial warmth. For 10,000 to 30,000 years, the world is warm. Ice is confined to Greenland and Antarctica. Forests spread north. Sea levels are high. Then the cycle begins again. This asymmetry slow freeze. Fast thaw creates the sawtooth shape. And it tells us something important. Ice sheets have their own internal dynamics. They do not just passively respond to orbital forcing. They have thresholds and feedbacks, tipping points. Once they start melting, the melting accelerates. We will see why in the next chapter. Once they start growing, they stabilize and resist change. The orbital cycles provide the pacing. They trigger the transitions. But the climate system, ice sheets and oceans and atmosphere, carbon cycle amplifies and shapes the response. This is why the match between orbital forcing and climate response is not simple. It is mediated by a complex, nonlinear system. But the underlying rhythm, the fundamental beat driving the whole dance, comes from the sky, from Earth's wobble and tilt and orbital stretch. Let us walk through the major interglacials revealed by ice and ocean cores. Each one is a variation on a theme: warm, ice-free, high sea levels, but each has its own character. Mice 1 Holocene present to 11,000. 700 years ago, the interglacial we are living in started with the end of the Younger Dryas cold snap. We will explore that dramatic event in episode 5. Unusually stable compared to previous interglacials, fewer climate oscillations, less variability. This stability likely enabled the development of agriculture and an eventually civilization. Emias Fiviemian, 130,000 to 115,000 years ago, the most recent interglacial before our own. Warmer than the Holocene global temperatures, 1–2 degrees Celsius higher than pre-industrial levels. Sea levels 6–9 meters higher, implying partial melting of Greenland and possibly West Antarctic ice sheets. Forests extended into regions now too cold to support them. Hippos in England. This warmth was driven by orbital configuration, high obliquity, strong seasonal contrast, combined with favourable precession northern summer at perihelion. The Eemian lasted about 15,000 years before sliding back into glaciation. MIS 7, 9 earlier interglacials, 240,000 and 330,000 years ago briefer, somewhat cooler than MIS 5 or MIS 1. These interglacials didn't achieve quite the same peak warmth, suggesting their orbital configurations were less favourable. The ice core record shows they still brought significant warming compared to the surrounding glacial periods. but they were shorter lived. MAS 11 400,000 years ago, perhaps the most interesting analogue for our own time. MIOS 11 was exceptionally long, possibly 30,000 years, and occurred during a period of low orbital eccentricity, just like today. Its sea levels may have been even higher than during the Eemian, suggesting more extensive ice sheet collapse. Some scientists argue that, without human greenhouse gas emissions, the Holocene might have followed a similar trajectory to MS 11, a prolonged, stable, warm period lasting tens of thousands of years. Each interglacial is unique because each arises from a unique combination of the three orbital cycles. No two interglacials have identical eccentricity and obliquity and precession alignments. The 100,000-year eccentricity cycle, the 41,000-year obliquity cycle, and the 19,023,000-year precession cycle overlap in ever-shifting patterns, creating interglacials of varying length and warmth and stability. But all share one characteristic: they are brief exceptions in a world dominated by ice. For the past 800,000 years, Earth has spent roughly 80-90 of its time in glacial conditions. Interglacials, warm periods like the one we are living in, are rare, fleeting interruptions, which brings us to a humbling realization: everything humans recognize as normal warm climates, high sea levels, forests stretching deep into northern latitudes, is actually the exception. The norm, the default state for the past million years, is a planet locked in ice. We live in a parenthesis. Now overlay human evolution onto this climate roller coaster. Modern humans, Homo sapiens, emerged roughly 300,000 years ago in Africa during MIS 9 and interglacial, but our species didn't stay confined to one climate state. Over the next 200,000 years, as the world oscillated between MIS 9 and 8 and 7 and 6 and 5, and eventually into the last glacial period, early humans experienced the full range of climatic extremes. Neanderthals lived through even more cycles. They evolved around 400,000 years ago during or shortly after MIS 11 and survived through multiple glacial interglacial transitions before going extinct roughly 40,000 years ago. Homo erectus, our more distant ancestor, spans an even longer timeline from about 9 million years ago to roughly 110,000 years ago. Erectus experienced dozens of glacial cycles, weathered the shift from 41,000-year rhythms to 100,000-year rhythms at the mid-Pleistocene transition, and adapted to climates ranging from tropical warmth to near glacial cold. All of human evolution, in other words, happened inside this orbital climate machine. Our ancestors didn't just passively endure these cycles, they adapted to them, evolved within them, and were shaped by them. The environmental pressures of oscillating climates may have driven brain growth, cultural innovation, and the behavioral flexibility that defines our species. We will explore this in depth in Series B. For now, the point is the Ice Age cycles are not just geological curiosities. They are the crucible in which humanity was forged. And now, having read the archives, having seen the rhythm in ice and mud, we understand the pattern. 8 cycles in 800,000 years. Slow freeze, fast thaw, driven by wobbles and tilts and orbital stretches too subtle to perceive, but profound enough to reshape continents. But a puzzle remains. The 100,000-year cycle dominates, even though eccentricity, the orbital parameter with that period, is the weakest direct forcing? How can the weakest cycle control the strongest response? To answer that, we need to dive deeper into the machinery. We need to understand not just the forcing, but how the climate system responds, how ice sheets grow and collapse, how carbon dioxide amplifies small changes, how thresholds and feedbacks transform gentle orbital nudges into massive climate swings. That is where we turn next. Picture a conference room in the mid-1970s. Fluorescent lights, coffee going cold in styrofoam cups, a projector humming in the back, casting graphs onto a screen at the front. The scientists gathered here have just done something remarkable. They've confirmed Milankovitch's theory. The ocean sediment cores show it clearly 41,000-year cycles, 23,000-year cycles, matching obliquity and precession. The orbital parameters predict climate. The 70-year-old hypothesis is vindicated. But as the presentation continues, someone in the third row shifts uncomfortably. Others lean forward, squinting at the graph. Because there is something else in the data. Something stronger than the obliquity signal. Stronger than the precession signal. A 100,000-year cycle, massive, dominating the climate record for the past million years. And it should not be there. Or rather it should be there, but barely, a whisper. Because eccentricity, the orbital parameter with a 100,000-year period, produces almost no direct change in the amount of sunlight Earth receives. It is the weakest of the three forcings. By a lot. Obliquity changes summer sunlight at 65 degrees and by about 60 watts per square meter. Precession changes it by up to 100 watts per square meter. But eccentricity, less than 5 watts per square meter. 1/20th the strength of precession, 1/12th the strength of obliquity. Yet in the ice volume record, the 100,000-year cycle is the loudest signal, the dominant rhythm, the beat that sets the pace for ice ages. Someone asks the obvious question, how can the weakest forcing produce the strongest response? Silence. Then murmurs. Then a realization spreading through the room. We've confirmed Milankovitch's theory, but we've also uncovered a paradox at its heart. This became known as the 100,000-year problem, and solving it would require rethinking everything about how ice sheets grow, how carbon dioxide amplifies climate, and how the Earth system transforms gentle nudges into dramatic swings. The eccentricity paradox let us quantify the mismatch. When Earth's orbit is most circular eccentricity near zero, the distance from Earth to the Sun varies by only about 3 over the course of a year. When the orbit is most elliptical eccentricity around 0.5, which is still pretty circular, that distance varies by about 11. The difference in total annual sunlight received by Earth between these two states is roughly 0.2. 0.2%. To put that in perspective, the change in summer sunlight at 65 degrees N due to obliquity swinging from 22.1 degrees to 24.5 degrees is about 60 watts per square meter. Roughly 13 variation in summer intensity. Precession, depending on eccentricity's amplitude, can change peak summer intensity by 100 watts per square meter at high latitudes. Eccentricity's direct effect on annual average insolation, about 24 watts per square meter globally, barely measurable, and yet When you analyze the ocean isotope records using spectral analysis, a mathematical technique that identifies repeating patterns in data, the 100,000-year frequency shows up as the strongest peak, not just present, dominant. Before 1 million years ago, this was not the case. In older climate records, the 41,000-year Obliquity cycle rules. Every 41,000 years, ice advances and retreats in rhythm with Earth's tilt. The climate dances to Obliquity's beat, which makes perfect sense. Obliquity is a strong forcing, directly affecting how much summer sun high latitudes receive. But then, around 1 million years ago, something shifted. The rhythm changed. The mid-Pleistocene transition, scientists call it. After this transition, the 100,000-year cycle dominates. Glacial periods last 80,000 to 100,000 years. Interglacials are brief 10,000 to 20,000 years. The sawtooth pattern we saw in Chapter 2 emerges. The orbital forcing didn't change. Earth's wobble and tilt and orbital stretch continued exactly as before, but the climate system's response changed. It started resonating with the weakest cycle. Why? In the 1970s and 1980s, this question vexed climate scientists. Some wondered if the calculations were wrong. They were not. The celestial mechanics are rock solid, confirmed by independent methods. Some proposed that eccentricity had hidden effects beyond changing total sunlight. This turned out to be partially correct. Others suggested it was not eccentricity at all, but some internal oscillation of the climate system that just happened to have a 100,000-year period. Also partially correct. The answer, as it emerged over decades of research, is subtle. Eccentricity doesn't drive the 100,000-year cycle through direct forcing. It paces it. It acts as a metronome, a regulator, a volume knob that modulates the strength of the other cycles. Here's how. Eccentricity as pacemaker. Remember from Chapter 1, eccentricity controls how elliptical Earth's orbit is. When eccentricity is high, Earth's distance from the Sun varies significantly over the year. When eccentricity is low orbit, nearly circular, the distance stays more constant. Now, here's the crucial point. Eccentricity modulates the amplitude of the precession cycle. Precession determines when in Earth's orbit the seasons occur. Currently, Northern Hemisphere summer happens when Earth is at aphelion farthest from the Sun. 13,000 years ago, Northern summer occurred at perihelion closest to the Sun. This difference matters because summer sunlight intensity at high latitudes affects whether ice can grow or melt. But how much it matters depends on eccentricity. If the orbit is circular, low eccentricity, perihelion and aphelion are almost the same distance from the Sun. The difference between summer when Earth is close versus summer when Earth is far is negligible. Precession's effect on seasonal intensity is weak. If the orbit is elliptical, high eccentricity, perihelion and aphelion differ substantially in distance. Now precession matters. Summer at perihelion means strong, intense summer sun. Summer at aphelion means weaker summer sun. The difference is significant, up to 100 watts per square meter at 65 degrees N, so eccentricity acts as a gain control. When eccentricity is high, precession's effects are amplified. When eccentricity is low, precession's effects are muted. This creates a pattern periods of strong insolation variability. When eccentricity is high and precession is favorable, alternate with periods of weak insolation variability. When eccentricity is low, These periods of weak variability last about 100,000 years. And here's where it gets interesting. Weak insulation variability gives ice sheets time to grow. Ice sheet internal dynamics. Ice sheets are not passive. They do not simply respond immediately to changes in sunlight. They have their own physics, their own internal behavior, their own memory. Think of an ice sheet as a system with inertia and thresholds. Inertia ice sheets take thousands of years to grow. Snow falls and accumulates, compresses into ice. The ice thickens and spreads, flows under its own weight. This process is slow. You cannot build a continental ice sheet in a few centuries. It takes tens of thousands of years of sustained cool summers that are not quite warm enough to melt the previous winter's snow. Once an ice sheet is large, it is stable. Its white surface reflects sunlight, keeping the region cool. The elevated ice surface creates its own weather patterns, channeling cold air. These feedbacks make the ice sheet resistant to melting. It takes sustained, strong warming to overcome this inertia and start collapse. Thresholds ice sheets do not grow linearly. They have tipping points. When the ice reaches a certain thickness, it starts flowing faster. When it reaches the ocean, it can buttress itself against the coastline, or it can surge into the sea and disintegrate. There are critical thresholds where small changes in forcing trigger large changes in ice sheet behavior. This creates what scientists call hysteresis. The threshold for starting to grow ice is different from the threshold for starting to melt it. You need less cooling to maintain an ice sheet than you needed to build it in the first place. Conversely, you need more warming to destroy an ice sheet than you needed to prevent it from growing. Now combine this with eccentricity pacing. When eccentricity is low orbit, nearly circular, precession has little effect. Summer insolation at high latitudes varies only weakly from one precession cycle to the next. There are no strong spikes of summer sun to melt growing ice. This is a window of opportunity for glaciation. Ice begins accumulating during the first few precession cycles within this low eccentricity window. Small ice caps form in favorable locations northeastern Canada and Scandinavia, Siberia. They survive multiple 23,000-year precession cycles because none of them brings quite enough summer sun to melt them completely. Each cycle, the ice persists and grows a bit more. Over 60,000 to 80,000 years, 3 or 4 precession cycles, the ice sheets expand. They merge and thicken, spread. They reach maximum extent and stability. Then eccentricity increases again. The orbit becomes more elliptical. Precession starts to matter, and when the next favorable precession alignment comes, northern summer at perihelion, the spike in summer insolation is strong enough to overcome the ice sheet's inertia, strong enough to trigger melt. The ice sheets collapse, not instantly, but relatively fast, 10,000 to 20,000 years. Positive feedbacks kick in, which we will explore next. The climate swings into an interglacial. The interglacial lasts as long as the insolation stays favorable. Then, when the next low eccentricity window arrives, the cycle begins again. This is how eccentricity paces the ice ages without directly forcing them. It is not the weak change in annual sunlight that matters. It is the modulation of precession's amplitude. Eccentricity sets the rhythm by creating windows of weak variability ice growth and windows of strong variability ice collapse. The 100,000-year climate cycle is the result of ice sheets accumulating slowly through multiple precession cycles during low eccentricity periods, then collapsing rapidly when eccentricity rises and precession delivers a strong summer insolation pulse. But there is another piece to this puzzle, another amplifier that makes the transitions dramatic: carbon dioxide. The role of carbon dioxide. Here's a fact that confused public understanding for years in ice core records. CO rises after temperature starts rising. Not before. After. By about 800 years, on average. Climate skeptics seized on this, arguing it proved CO doesn't cause warming. If temperature leads and CO follows, how can CO be the driver? The argument misses the point. During Ice Age cycles, CO is not the initial driver. Orbital forcing is. But CO acts as an amplifier, a feedback. And the lag actually makes perfect sense when you understand the mechanism. Here's what happens during a deglaciation step. One orbital forcing triggers initial warming. Summer insolation at 65 degrees N increases due to favorable precession alignment during a period of rising eccentricity. Northern hemisphere ice sheets begin melting at their margins. The warming starts in the northern hemisphere, particularly in areas directly influenced by changing ice sheets. Step 2, Southern Ocean responds. Changes in northern ice sheets affect global ocean circulation. The Atlantic Meridional Overturning Circulation, AMO, the conveyor belt that moves heat around the planet, responds to meltwater pulses. This affects the Southern Ocean around Antarctica. The Southern Ocean begins warming. Step 3, CO is released from the ocean. Cold water holds more dissolved CO than warm water. As the Southern Ocean warms, it releases CO to the atmosphere, much like a warming soda releases its fizz. This process is not instant. It takes centuries for deep ocean water to circulate to the surface and outgas. Hence the 800-year lag. Step 4, CO amplifies the warming. Once CO levels rise in the atmosphere, the greenhouse effect kicks in. More CO means more heat trapped. This amplifies the initial orbital forcing. Temperatures rise faster. More ice melts. More ocean warms. More CO is released. A positive feedback loop. Step 5, the warming spreads globally. The CO-driven warming affects the entire planet, not just the high northern latitudes where orbital forcing is strongest. The ice sheets respond not just to the orbital trigger, but to the globally amplified warming. This is why deglaciations are so dramatic. The initial orbital nudge gets multiplied by the CO feedback. Without the CO amplification, ice ages would be far less pronounced. Models suggest CO, along with other greenhouse gases like methane and nitrous oxide, accounts for roughly half of the total glacial to interglacial temperature swing. The orbital forcing provides the initial trigger and the timing, but greenhouse gases provide much of the power. This is why the temperature leads CO relationship doesn't contradict the greenhouse effect. CO doesn't initiate the warming during natural deglaciations, but it sustains and amplifies it. Think of it like pushing a swing. You provide the initial push orbital forcing, but the swing's momentum CO feedback carries it much higher than your push alone could. Going into a glacial period, the relationship reverses. Temperature drops first due to declining summer insolation, and CO follows, but with a longer lag. The ocean slowly reabsorbs CO as it cools. Expanding ice sheets and changes in vegetation also draw down atmospheric CO. The cooling is less abrupt than the warming because there is no rapid collapse, just slow, steady ice accumulation and gradual CO decline. The CO story reveals something: crucial ice age cycles are not driven by simple, direct forcing. They emerge from complex interactions between orbital forcing, ice sheet dynamics, ocean circulation, and the carbon cycle. The system is non-linear. Small inputs can produce large outputs. Weak forcings can control strong responses. Which brings us to the next piece. Why did the system's behavior change a million years ago? Nonlinear dynamics and tipping points, linear systems are predictable. Double the input, you double the output. Straightforward, proportional. Earth's climate is not linear. In nonlinear systems, small changes can trigger large responses. Thresholds exist where the system's behavior abruptly shifts. Feedbacks amplify initial perturbations, and the relationship between cause and effect can be anything but proportional. Ice age cycles are a textbook example of nonlinear climate dynamics. Consider the asymmetry we've seen throughout these chapters: slow descent into glaciation, rapid climb out. Ice grows over 60,000 to 80,000 years. Ice melts in 10,000 to 20,000 years. Same orbital forcing on the way up and the way down, but radically different response times. Why? Positive feedbacks during melting. Once ice starts melting, several feedbacks accelerate the process. Albedo feedback: white ice reflects sunlight. Dark land and ocean absorb it. As ice melts and exposes darker surfaces, more heat is absorbed, accelerating melt. Elevation feedback: the top of an ice sheet is cold, high altitude, low temperature. As the sheet thins, its surface drops to lower, warmer elevations. This increases melt rates. Ice dynamics: once an ice sheet starts collapsing, especially if it is resting on bedrock below sea level marine ice sheet instability, the collapse can accelerate. Ocean water can undercut the ice from below, causing rapid disintegration. CO release as discussed. Warming oceans release CO, which amplifies warming globally, which accelerates ice melt. These feedbacks do not operate in reverse during ice growth. Building ice doesn't trigger equivalent positive feedbacks. It is more of a steady accumulation process. Hence the asymmetry. Thresholds and tipping points. The climate system has critical thresholds. Cross them, and behavior changes abruptly. During glacial inception, the start of an ice age, there is a threshold of summer insolation below which snow can survive year-round at high latitudes. Once sustained cooling drops insulation below this threshold, ice begins accumulating, but the exact threshold varies depending on CO levels, ocean circulation, and existing ice coverage. During deglaciation, there are thresholds for ice sheet collapse. Once summer insulation rises above a certain level, melt rates exceed accumulation rates, and the ice sheet begins shrinking. But once shrinking starts, the feedbacks can push the system past a point of no return. Even if insulation subsequently declines, the ice may continue melting due to internal dynamics. This creates the possibility of irreversible transitions. You can push the climate into a state from which it will not return even when the forcing is removed. The ice sheets do not have perfect memory. They cannot always recover their previous extent. The role of stochastic resonance, one elegant explanation for the 100,000-year cycle, involves a concept from physics called stochastic resonance. Here's the idea: weak periodic signals can be amplified by noise in a nonlinear system. The climate system has internal variability, weather fluctuations, ocean circulation wobbles, random events. This is noise. Normally, noise obscures weak signals, but in systems with thresholds, noise can actually help a weak periodic signal trigger threshold crossings. Imagine a ball in a valley with two wells separated by a small hill. The ball sits in one well. A weak periodic push like eccentricity's forcing is not strong enough to move the ball over the hill into the other well. But add random jostling climate noise, and occasionally the jostling will coincide with the periodic push, giving the ball enough energy to cross the threshold. In the climate system, the weak eccentricity cycle combined with internal climate variability and the stronger but faster precession and obliquity cycles can create stochastic resonance. The 100,000-year signal gets amplified through the system's nonlinear response. This is why ice ages are both regular and unpredictable in their details. The 100,000-year pacing is robust. You can predict roughly when the next ice age would start absent human influence. But the exact size and duration and character of each glaciation depends on the specific alignment of all three orbital cycles: the state of the carbon cycle, ocean circulation, and internal climate variability. Putting it all together. So here's the answer to the 100,000-year problem. Eccentricity doesn't drive ice ages through direct forcing. It paces them by modulating the strength of precession. When eccentricity is low, precession's effects are weak, giving ice sheets time to grow through multiple 23,000-year cycles. When eccentricity rises, precession's effects strengthen, eventually delivering enough summer sun to trigger deglaciation. Ice sheets have their own internal dynamics, inertia, and thresholds, preferred time ice scales. They accumulate slowly and collapse quickly because feedbacks operate asymmetrically. CO acts as an amplifier, not an initial driver. It follows temperature during natural climate cycles, but magnifies the warming or cooling once triggered. The climate system crossed a threshold around 1 million years ago, the mid-Pleistocene transition, possibly due to declining CO, changing ice sheet geography, or both. After this transition, the system began resonating with the 100,000-year eccentricity pacing. The result is a complex, nonlinear response to relatively simple orbital forcing. The weak eccentricity cycle sets the rhythm, not through brute strength, but through clever timing by controlling when the stronger precession forcing matters most. It is a climate engine, yes, but not a simple one. Not a machine where you turn a dial and get a proportional response. It is a system with memory and thresholds and feedbacks and tipping points. A system where the weak can control the strong, where timing matters more than magnitude, and where small nudges can trigger avalanches. And now we understand not just that ice ages happen, but how they happen. We understand the machinery, the gears, the levers, the feedback loops. But understanding the machinery is one thing. Witnessing it in action is another. To truly grasp what these orbital forces mean not as numbers on a graph, but as lived reality, we need to zoom into specific moments. Stand at the threshold. Watch as the cosmic gears align and the world transforms. That is where we turn next to the moments of transition, to the times when orbital forcing, ice sheet dynamics, and carbon feedbacks converge to end ice ages and birth new worlds. When glaciers that had stood for 80,000 years began to melt, seas began to rise, and the map of Earth was redrawn. We will watch the last great thaw. We will see what happens when the climate engine shifts gears in real time. southern France, 18,000 years ago. The Franco-Cantabrian Refugium, one of the last places in Europe where humans can survive. An elder sits outside a cave entrance, wrapped in mammoth hide against wind that cuts like flint. The fire burns low. She is 60 winters old, ancient by the standards of this world. Her grandmother's grandmother's stories echo in her memory tales of warmer times, forests where now only tundra grows, animals that no longer come. But those are just stories, distant, abstract, like speaking of stars. This is what she knows cold. The ice visible on the northern horizon, a white wall that never retreats. Winters so brutal that entire bands disappear. Summers barely warm enough to melt the permafrost. A landscape of stone and lichen and stunted willow, where every calorie is earned with risk. The caribou migrations dictate everything. When they come, her people eat. When they do not, her people starve. This year the herds arrived late, smaller than before. Hunters tracked them farther north than is safe, to the very edge of the ice. She has lived her entire life in the shadow of that ice. Her children have. Her grandchildren will. What she cannot know, what no human alive can know, is that everything is about to change. 300 kilometers north, buried beneath 3,000 meters of ice, the physics of the Laurentide ice sheet are shifting. The ice has reached maximum extent. For 60,000 years it has been growing, creeping south through countless 23,000-year precession cycles, building mass during a period when Earth's orbit was nearly circular and summer sunlight too weak to melt the accumulated snow. But the orbital configuration is changing. Earth's orbit is becoming more elliptical. The wobble of its axis is bringing northern hemisphere summer back toward perihelion, the point when Earth passes closest to the sun. And tilt is increasing, directing more summer sunlight toward high latitudes. The numbers are small, a few percentage points of variation in summer insolation at 65 degrees N. But after 60,000 years of ice growth, a few percentage points are enough. The ice sheets have reached their tipping point. Within 1,000 years, maybe less the margins will begin retreating. Slowly at first, meltwater channels carving through ice that has stood for millennia. Then faster, then catastrophically, as feedbacks kick in and the white shield fractures. But that is generations away. Too far in the future for anyone alive to witness the transformation. The elder pulls the hide tighter, stirs the fire, watches her grandchildren sleep. Tomorrow they'll track the caribou again, repair the stone tools, gather what fuel they can find in this treeless waste, survive another day in a world that has been cold for as long as anyone can remember. The stars turn overhead. The same stars her grandmother's grandmother saw. The orbital engine is shifting gears, but on timescales invisible to human eyes. She doesn't know that the world her great-great-grandchildren inherit will be unrecognizable. That forests will return to lands that have been tundra for 50,000 years. That the ice will retreat so far north that entire new continents will emerge. That the herds will change, the climate will warm, and everything her people know about survival will need to be relearned. She doesn't know she is living at the cusp of termination, the last great thaw, the end of the ice age. All she knows is cold, and that the caribou came late this year. The fire crackles. The ice gleams on the northern horizon, eternal and unmoved. But beneath the surface, in ways too subtle to feel, too slow to see, The machinery is turning. Termination, what scientists call the transition from the last glacial maximum into our current interglacial, is the climate transition we know in the most detail. We've drilled it in ice cores, cored it in ocean sediments, mapped it in coral reefs, traced it in cave formations. We can see not just the broad sweep, but the intricate steps, the stutters and surges, the moments when the climate lurched forward and the moments when it hesitated. Here's what happened 26,000 to 19,000 years ago, was the last glacial maximum, LGM, the peak of the ice. The Laurentide ice sheet smothered Canada and reached as far south as New York City and Chicago. The Fennoscandian ice sheet buried Scandinavia under ice 3 kilometers thick. Smaller ice caps crowned the Alps, the Pyrenees, the Rockies. Global sea level stood 120 meters lower than today. The exposed continental shelves became land Beringia connecting Asia and North America, Sunda joining Southeast Asian islands into a supercontinent, Doggerland bridging Britain to Europe. Earth was locked in deep freeze. Atmospheric CO had dropped to 180 parts per million, the lowest it had been in 800,000 years. The planet was dusty and dry, cold. Average global temperatures were 4-7 degrees Celsius cooler than pre-industrial levels, with high latitudes 10-15 degrees Celsius colder. Then, around 19,000 years ago, something shifted. The orbital configuration, look at the orbital parameters. By 19,000 years ago, the alignment was changing from the configuration that had built the ice to the configuration that would melt it. Eccentricity was increasing. Earth's orbit was becoming more elliptical, which meant the distance between perihelion closest approach to Sun and aphelion farthest point was growing. This amplified Precession's effects. Precession was bringing northern hemisphere summer back toward perihelion. 13,000 years earlier, at the height of glaciation, northern summer had occurred at aphelion when Earth was farthest from the Sun. Now the wobble was reversing. Northern summers would get progressively stronger as they shifted toward occurring when Earth was closest to the Sun. Obliquity, Earth's axial tilt, was increasing, moving from the minimum tilt that had characterized much of the glaciation toward higher tilt values. This directed more summer sunlight to high northern latitudes. The result summer insolation at 65 degrees N began climbing. Not dramatically, this was not an instant switch, but steadily. The trend that had favored ice growth for 60,000 years was reversing, and the ice sheets, having reached maximum size, were primed to respond. The initial melt 19,000, 15,000 years ago, the first signs were subtle. Ice sheet margins in southern sectors, where summer temperatures reached the melting threshold, began retreating. Meltwater rivers that had been sluggish trickles became torrents each summer. The ice stopped advancing. Global sea level began rising. Slowly at first, maybe a few millimeters per year. Coastlines shifted imperceptibly, but compound that over centuries and it becomes meters. Over millennia, tens of meters. CO levels started increasing. Remember, CO follows temperature during natural deglaciations. As the Southern Ocean began warming through mechanisms we will explore, it released dissolved CO that had been stored in deep waters during the glacial. The lag was about 800 years' time for ocean circulation to transport heat and trigger outgassing. By 18,000 years ago, the process was underway. ice volume was declining. Temperatures in Antarctica were rising. SUO was creeping upward from its glacial minimum of 180 ppm toward 190, then 200 ppm, but this was gradual warming, a slow unwinding, the kind of change you might track across several human lifetimes if you kept detailed records, which Ice Age peoples didn't. Then came the acceleration. The Beeling-Ala-D interstadial 14,000, 712,900 years ago, around 14,700 years ago, something dramatic happened. The North Atlantic region lurched into warmth. Greenland temperatures jumped by 10-15 degrees Celsius within a few decades. Some ice core records suggest the shift happened in less than 10 years. Tree species that couldn't survive in tundra suddenly appeared in Scandinavia. Lakes that had been frozen year-round melted. The transformation was rapid enough to be visible within a single human lifetime. This event, called the Beeling-Ala-D interstadial, named after sites in Denmark where evidence was first found, raised northern temperatures to near modern levels almost instantly. What triggered it? The Atlantic Meridional Overturning Circulation AMO key restarted. During Heinrich Stadial 1, the period just before Beeling-Ala-D, the ocean had developed a strange configuration. Deep North Atlantic waters were actually warmer than surface waters, an inverted temperature profile that cannot happen unless something is preventing normal mixing. Warm, salty water from the Southern Ocean had been accumulating at depth, trapped beneath a lid of cold, fresh meltwater at the surface. This was ocean potential energy building up, heat stored but not released, then possibly triggered by changes in ice sheet meltwater flow, possibly by reaching a tipping point in the system the lid broke. The deep warm water surged upward. Ocean convection restarted. The AMOC, which transports enormous amounts of heat from the tropics to high northern latitudes, switched back on. The effect was instantaneous, geologically speaking. Within decades, the northern hemisphere warmed dramatically. But here's the crucial detail: this warming was almost entirely confined to the northern hemisphere. The southern hemisphere actually cooled during Beeling-Ala-D. This is the bipolar seesaw. When the AMOC is strong, it pulls heat from the south and dumps it in the north. Southern cooling, northern warming. The Beeling phase, the initial warming, lasted about 600 years. Then came a brief cold snap called the Older Dryas, about a century long, not observed everywhere. Then the Ala-D phase, another warm interval lasting until about 12,900 years ago. During this time, ice sheets were collapsing fast. Meltwater pulse won a coral reefs offshore from Tahiti record, a stunning event around 14,600 years ago. Sea level rose between 14 and 18 meters in less than 340 years. That is 4-5 centimeters per year, 50 times faster than current sea level rise, fast enough that coastal communities would need to relocate every few generations. Islands disappeared. Shorelines moved kilometers inland. This is called Meltwater Pulse 1A, MWP-1A. Where did all that water come from? Both Antarctica and North America contributed. The exact proportions are still debated, but most evidence points to significant Antarctic contribution, possibly from the West Antarctic ice sheet, which is vulnerable to marine ice sheet instability. When ice resting on bedrock below sea level starts melting, ocean water can undercut it from below, triggering rapid collapse. The North American contribution likely came from saddle collapse, when an ice sheet grows so large that it develops multiple domes separated by saddles. If the saddle melts through, the ice sheet can rapidly reorganize, shedding mass as the domes separate. The crucial point MWP1A demonstrates that ice sheets can collapse far faster than they grow. The slow accumulation of 60,000 years can be partially undone in centuries when the right conditions align. The Younger Dryas interruption 12,911,700 years ago, just when the deglaciation seemed to be proceeding smoothly, the climate lurched back toward cold. Around 12,900 years ago, temperatures in the northern hemisphere plummeted. Not back to full glacial conditions, but close. Greenland cooled by 10-15 degrees Celsius. Glaciers in Europe and North America re-advanced. Forests that had spread into Scandinavia retreated. The Dryas octopetala flower, an Arctic alpine species characteristic of tundra, became abundant again across Europe. This event, the Younger Dryas, lasted about 1,200 years. What caused it? The scientific consensus points to AMO shotdown. Again, the mechanism, as the Laurentide ice sheet melted, it created enormous glacial lakes, dammed by the ice itself. The largest was Lake Agassiz, which covered much of central Canada. This lake was the size of the Black Sea and Caspian Sea combined, filled with glacial meltwater. Around 12,900 years ago, the ice dam broke, or the drainage route shifted. Suddenly, an enormous pulse of fresh water flooded into the North Atlantic, probably via the Mackenzie River initially, though the exact route is debated. Fresh water is less dense than salty ocean water. When you dump enough of it into the North Atlantic, it forms a lid on the surface, preventing the dense, salty water beneath from sinking. No sinking means no deep water formation. No deep water formation means the AMO shuts down. And when the AMO shuts down, the northern hemisphere cools dramatically. The heat that had been transported north stays in the tropics and southern hemisphere instead. So the Younger Dryas represents the last gasp of glaciation. A brief return to near glacial conditions, driven not by orbital forcing, but by the chaotic dynamics of melting ice sheets disrupting ocean circulation. It is a reminder that deglaciation is not smooth. It is messy. Ice sheets do not just melt gradually, they collapse in bursts, flooding the ocean with meltwater, disrupting circulation, triggering climate whiplash. The final warming 11,700 years ago, the Younger Dryas ended as abruptly as it began. Around 11,700 years ago, with precision measured in ice core annual layers, Greenland warmed by 10 degrees Celsius in perhaps 50 years. Some records suggest even faster a decade. The AMO restarted. Northern Hemisphere temperatures surged. The last remnants of Ice Age climate vanished. This marks the beginning of the Holocene, our current interglacial. The warm, relatively stable period in which all of recorded human civilization has unfolded. The ice sheets continued melting for thousands of years after this. The Laurentide ice sheet finally disappeared around 7,000 years ago. Sea level kept rising until about 6,000 years ago, by which time it had climbed those full 120 meters from LGM minimum to near modern levels. But the major transition, the shift from glacial to interglacial climate, was complete by 11,700 years ago. Termination, I took about 8,000 years, start to finish 19,000, to 11,000 years ago. But the dramatic warming happened in pulses. The Bolling-Alerod jump at 14,700 years ago, the final Holocene warming at 11,700 years ago. Between them, the Younger Dryas interruption. Sawtooth in reverse, slow cooling punctuated by fast warming, but with stutters and false starts along the way. Last time Earth was, this warm step back further. Not 20,000 years, but 130,000. Marine isotope stage 5. The Eemian interglacial. The last time Earth experienced interglacial warmth before our own Holocene. This was the previous cycle. The last time the orbital machinery aligned to melt ice sheets, warm the planet, and create conditions similar to what we experience today. Studying the Eemian is like looking at a preview of natural climate states Earth can occupy, and it reveals something unsettling. The Eemian was warmer than the Holocene, noticeably so. When it happened, how warm it got. The Eemian lasted from approximately 130,000 to 115,000 years ago, about 15,000 years, making it longer than the Holocene has been so far. We are only 11,700 years into our interglacial. Peak warmth occurred around 125,000 years ago. Global mean temperatures were comparable to pre-industrial Holocene levels, but with crucial regional differences. High northern latitudes were significantly warmer than today. Summer temperatures in the Arctic were 4-5 degrees Celsius higher than pre-industrial levels. Annual mean temperatures in northern Finland and Scandinavia were 2-3 degrees Celsius warmer. Sea level tells the story most dramatically. The Eemian Sea stood 6 to 9 meters higher than present. Let that sink in. 6 to 9 meters. That is 20 to 30 feet. Not from some distant hothouse climate millions of years ago, but from the most recent interglacial before ours, when orbital forcing was different, but CO levels were similar to pre-industrial around 280 ppm. Where did that extra water come from? Greenland's ice sheet partially melted. Parts of the West Antarctic ice sheet likely collapsed. Both ice masses contributed to raising global sea level well above anything modern civilization has experienced. The rate of rise was not uniform. Coral evidence from fossil reefs suggests periods when sea level jumped 1.6 meters per century, a rate that would be catastrophic for modern coastal infrastructure. The orbital configuration that caused it why was the Eemian warmer than the Holocene despite similar CO levels. Orbital parameters. The Eemian occurred during one of the most extreme orbital configurations of the past million years. Eccentricity was relatively high. Earth's orbit was more elliptical than today. This amplified the effects of precession significantly. Obliquity peaked at about 24. 2 degrees near the maximum of its range. Higher tilt meant more summer sunlight at high latitudes and stronger seasonal contrasts. Crucially, it meant the Arctic received more direct summer sun, helping to melt ice and warm polar regions. Precession aligned northern hemisphere summer with perihelion. This is the opposite of today. Currently, northern summer occurs when Earth is at aphelion farthest from sun. During the Eemian peak, northern summer occurred when Earth was closest to the sun, creating unusually intense northern summers. The combined effect summer insolation at 65 degrees N reached about 490 watts per square meter, compared to about 450 WN today. That is roughly 7-9 more summer sunlight hitting the critical latitude where ice sheets form. This was enough to drive Greenland ice melt and push Arctic temperatures well above modern levels. The southern hemisphere, and conversely, experienced slightly cooler summers due to the precession phase. When one hemisphere gets stronger seasons, the other gets weaker. The Eemian is often held up as a potential analogue for our future because it shows what Earth looks like when polar regions warm substantially. The orbital forcing was different from what we are experiencing. Now we are adding CO rather than getting more summer sun, but the regional warming patterns and ice sheet response provide valuable insights. What the world looked like, the Eemian Earth was a different planet. In Europe, forests extended far into what is now Arctic tundra. Trees grew at North Cape, Norway above 71 degrees M, well inside the Arctic Circle, where today only tundra survives. Hardwood species like hazel and oak thrived in Oulu, Finland. The tree line pushed hundreds of kilometers north of its current position. Scandinavia was an island. Sea levels 6-9 meters higher meant the Baltic Sea connected to the White Sea, cutting off Fennoscandia from mainland Europe. The Baltic itself was much saltier than today, closer to Atlantic salinity, because the connection to the ocean was deeper and wider. The fauna was spectacular. This is one of the most evocative details during the Eemian. Hippopotamuses lived in England. Fossil evidence shows Hippopotamus amphibius, the same species, alive today, ranging as far north as North Yorkshire. Not just Britain, they reached the Rhine Valley in Germany. Straight-tusked elephants, Paleoloxodon antiquus, roamed across Europe, including regions that are now cold-temperate. Lions and hyenas and leopards hunted in what is now northern Europe. The fauna was more similar to modern sub-Saharan Africa than to anything Europeans would recognize today. North Africa was green. The Sahara experienced a humid phase during the early Eemian. Lake Chad expanded to enormous size. Vegetation covered regions now barren desert. This green Sahara was driven by intensified African monsoons, a response to the increased northern hemisphere summer insolation. Sea level changes reshaped geography. Coastlines lay kilometers inland from modern shores. Many current islands were submerged. Florida's coastline retreated inland. Low-lying river valleys became marine embayments. Coral reefs that formed during the Eemian now sit 6-9 meters above current sea level on tectonically stable coastlines, marking the high water stand. The Mediterranean experienced unusual conditions. The warmer climate and altered ocean circulation patterns affected regional sea surface temperatures and precipitation. Some records show periods of weakened Atlantic meridional overturning circulation during the Eemian, creating cold phases in the North Atlantic, even while global temperatures remained elevated. Human context, who witnessed this world? Neanderthals, Homo neanderthalensis, were at their peak during the Eemian. They'd been in Europe for hundreds of thousands of years, evolved specifically for Ice Age conditions, yet they adapted to Eemian warmth. Archaeological sites from Mewais Five show Neanderthals hunting the warm climate megafauna, living in forests rather than tundra, adjusting their tools and strategies for a different world. Early modern humans, Homo sapiens, existed during the Eemian, but were still primarily in Africa. Our species evolved around 300,000 years ago in Africa, and by 130,000 years ago, We had reached the Levant. There is evidence of early modern humans in Israel during the Eemian, but we hadn't yet made our major expansion out of Africa. That would come later, during the subsequent glacial period. So 2 human species experienced the Eemian warmth: Neanderthals in Europe and Western Asia, moderns in Africa, and sporadically in the Near East. Both survived it. Both adapted. The Eemian proves that human species, both Neanderthals and ourselves, can handle warmer climates than the Holocene average. It is rapid change that is dangerous, not specific temperature levels per se. Why it ended nothing lasts forever, especially not interglacials. The orbital parameters that created Eemian warmth were temporary. By 120,000 years ago, the configuration was changing. Obliquity began declining from its peak. Less tilt meant less summer sunlight at high latitudes. Precession continued its 26,000-year wobble. Northern summer moved away from perihelion back toward aphelion. Summers weakened. Eccentricity began its slow decline toward more circular orbit, which would eventually mute precession's effects entirely, though this takes 100,000 years. Summer insolation at 65 degrees N dropped, gradually at first. Snow that melted completely in the early Eemian began persisting through summer in favored locations: high altitude valleys, north-facing slopes, regions receiving lake effect snow. By 115,000 years ago, perennial snowfields were forming in Scandinavia and northeastern Canada. These were not full ice sheets, yet just patches that survived summer. But they were seeds. The Eemian ended not with a bang, but with a slow fade. Temperatures declined, forests retreated, cold-adapted species moved south. The hippos and elephants of Britain disappeared likely before they froze. Populations probably shifted south or went extinct as ecosystems changed. By 110,000 years ago, the climate had cooled enough to mark the end of the interglacial. The world entered MIS 5 cooler period, though not yet a full glacial. The slide back toward Ice Age conditions had begun. The transition from Eemian warmth to the subsequent glaciation took about 15,000 years, much slower than the rapid warming that began the interglacial. This is the asymmetry we keep seeing: fast warming driven by tipping points and feedbacks, slow cooling driven by gradual orbital changes and ice accumulation. Lessons from the Eemian. The Eemian is studied intensely today because it is the most recent period when Earth was as warm as, or warmer than, the present. Climate scientists use it to test models, understand ice sheet behavior, and gauge how much sea level rise we might expect from a given amount of warming. Key insights: ice sheets are sensitive, with temperatures only 1-2 degrees Celsius warmer than preindustrial, and high latitude temperatures 3-5 degrees Celsius warmer. Greenland lost enough ice to contribute 4 meters to sea level. The West Antarctic ice sheet likely contributed another 4 meters. This suggests that the ice sheets currently containing enough water to raise sea level by 65 meters Greenland Antarctica combined can partially collapse with relatively modest warming. Sea level rise lags temperature. The Eemian sea level peak occurred 125,000 years ago, several thousand years after initial warming began. Ice sheets take time to melt. This lag means we are committed to ongoing sea level rise. Even if we stabilize temperatures, the ice sheets are playing catch-up with current warming. Regional patterns matter. The Eemian was not uniformly warm everywhere. Some regions experienced cooling events even during the interglacial peak. Climate is complex, with regional variability superimposed on global trends. Interglacials are brief. The Eemian lasted 15,000 years. Most Pleistocene interglacials last 10,000, 30,000 years. Glacials last 60,000, 100,000 years. Earth spends most of its time in the cold state. Warm periods like the Eemian or our Holocene are precious anomalies. The opposite transition we've watched ice melt, now watch it grow. Glacial inceptions, the transitions from interglacial warmth to ice age cold, are the mirror image of terminations, but slower and subtler. There is no dramatic pulse, no abrupt jump, no meltwater pulse 1A in reverse, just a slow, relentless accumulation. Understanding how ice ages begin tells us something: crucial ice sheets do not need catastrophe to form. They do not require volcanic winters or asteroid impacts or sudden climate flips. They just need sustained, cool summers at high latitudes. Give Earth a few tens of thousands of years of summers that are not quite warm enough to melt the previous winter's snow, and ice will pile up until it becomes a continent drowning sheet. The last inception after the Eemian let us trace the most recent glacial inception, the one that followed the Eemian and led to the ice age our ancestors survived. Around 115,000 years ago, the Eemian interglacial was waning. Summer insolation at 65 degrees N had declined from its peak. Obliquity was decreasing, Earth's tilt reducing from 24 degrees toward 23 degrees. Precession had moved northern summer away from perihelion. The orbital configuration that created Eemian warmth was gone, the first sign snow persisting through summer in favoured locations. Not everywhere. Not even most places. But in northeastern Canada, the Labrador Peninsula, and in Scandinavia, small snowfields began surviving the melt season. These were zones where local geography enhanced cooling high elevations, north-facing slopes, regions downwind of cold ocean currents. Year 1, a patch of snow survives summer. Year 2, new snow falls on old snow. The patch grows. Year 10, the snowfield is thicker. Its white surface reflects more sunlight, keeping the region cooler. More snow accumulates. The MIS 5D 5A oscillations, but here's where it gets interesting. The descent from Eemian warmth into full glaciation was not smooth. The climate oscillated. Marine isotope stage 5 is subdivided into lettered phases MIS 5E 100 and 30 115 Ka, the Eemian peak. Full interglacial. MIS 5D 100 and 15 105 Ka cooling. Ice beginning to form. But not yet a full glacial, more like halfway there. MIS 5C 100 and 593 Ka brief warming, temperatures rose again, approaching but not reaching Eemian levels. The small ice caps that formed during 5D may have partially melted. MIS 5B 90 385 Ka cooling again, ice re-expanding. MIS 5A 85 75 another warm spike. In Britain, this is called the Brimpton interstadial, warm enough for forests to spread into regions that had been tundra during 5D and 5B. MIS 475-60 now the serious cooling begins. Transition into full glacial conditions. MIS 360-30 Ka unstable glacial period with oscillations Dansgaard-Oeschger events. MIS 230-12 full glacial, culminating in last glacial maximum at 2620 Ka. So the inception took roughly 100,000 years from end of Eemian to full glaciation. But it was not linear. It stuttered. The climate attempted to return to interglacial warmth several times during 5C and 5A, but couldn't quite make it. Each time cooling resumed. Why the oscillations? Precession cycles. Even as the overall orbital trend favoured cooling due to declining obliquity and eccentricity, Precession continued its 23,000-year wobble. Every 11,000 years, it would bring northern summer back toward perihelion, creating brief warm pulses. But these were not strong enough to fully melt the ice that had accumulated. They just slowed the descent. The sawtooth pattern again, but inverted instead of slow cooling punctuated by rapid warming, the termination pattern. Inception shows slow cooling punctuated by brief warm intervals that fail to reverse the trend. How ice accumulated let us zoom into the mechanism. Location matters. Ice doesn't form everywhere at once. It begins in specific nucleation zones, places where local climate and geography favour snow accumulation: northeastern Canada, Labrador, Baffin Island, Keewatin, Scandinavia, particularly northern Sweden and Norway, Siberia, Taimyr Peninsula, and surrounding regions, Iceland, Greenland, which never fully deglaciated even during Eemian. In these zones, winter snowfall exceeds summer melting. The mass balance is positive. Snow accumulates. Thickness drives spreading. As snow piles up and compresses into ice, the ice cap thickens. Once it reaches 100 meters thick, the ice begins flowing under its own weight. It spreads outward from the accumulation zone like very slow molasses. This creates a positive feedback as the ice sheet expands to lower latitudes and elevations. Its white surface reflects more sunlight albedo effect, cooling the region further, allowing the ice to advance even more. Coalescence. Initially, there are separate ice caps in each nucleation zone, but as they expand, they merge. The Keewatin and Labrador ice caps join to form the Laurentide ice sheet. Scandinavian and Siberian ice to a lesser extent merge into the Fennoscandian ice sheet. By 70,000 years ago, there were recognizable ice sheets covering millions of square kilometers. By 30,000 years ago, they were approaching their maximum extent. Why inception is slow. Unlike terminations, there is no sudden trigger for ice growth. No meltwater pulse 1A in reverse. No abrupt AMO key restart flooding the north with warmth. Ice simply accumulates year by year. The process is limited by snowfall rates. You can only add as much ice as the atmosphere can deliver as snow. Even in favourable locations, snowfall is measured in meters per year at most. Accumulate a few meters per year for 10,000 years and you get 30,000 meters worth of ice, but compression and flow limit actual thickness to a few kilometers. Furthermore, there are negative feedbacks that slow the process. Isostatic depression. As ice piles up, its weight pushes the underlying crust downward into the mantle. This creates a depression. The surface of the bedrock drops, putting the ice base at lower elevation, where temperatures are warmer. This limits how thick the ice can grow in any one place. Flow limits: the thicker the ice, the faster it flows outward. Eventually, you reach a balance where ice flowing away from the accumulation zone equals ice being added by snowfall. The ice sheet reaches an equilibrium thickness. Ocean and atmospheric feedbacks. Growing ice sheets change atmospheric circulation patterns. They create high-pressure zones over the ice, which can deflect storm tracks, reducing snowfall. They cool the nearby ocean, which can reduce evaporation and thus snowfall. These feedbacks mean ice growth follows a law of diminishing returns. The first kilometre of ice builds relatively fast. The second kilometre takes longer. Getting to 3 kilometres, thick like the ice at the LGM requires many tens of thousands of years. Human experience of inception, what did this feel like for people living through it? An individual human would not notice. Glacial inception happens on multi-generational timescales, but over 20-30 generations. The landscape transforms. Imagine a lineage living in what's now southern Germany. At the time of the Eemian MIS-5E, their ancestors hunted straight-tusked elephants in deciduous forests. The climate was Mediterranean warm and mild, with abundant game. 20 generations later MIS-5D, 110,000 wire forests are thinning. Winters are harsher. The elephants have moved south. Reindeer are appearing cold-adapted species, moving in as warm-adapted ones retreat. 40 generations MIS-5B, 90,000 YA tundra is replacing forest in the north. Permafrost is forming. Summers barely melt the winter snow in high valleys. Glaciers are visible on the Alps, larger than they've been in living memory or in any memory. 80 generations MIS-4, 70,000 year. The region is now marginal for human habitation. Cold steppe dominates. Megafauna are adapted to ice age conditions: mammoths, woolly rhinos, musk oxen. The band has moved south or adapted to cold climate survival strategies. 150 generations MIS-2, LGM, 25,000 year, the region is under ice, uninhabitable. Human populations have compressed into southern Refugia, Spain and Italy. The Balkans, France south of the Loire. That is the arc of glacial inception from a human perspective. Not apocalyptic, not sudden. Just a slow, relentless shift toward harsher conditions, forcing adaptation or migration every few millennia. The crucial difference from terminations during deglaciation. Change happens fast enough that a single elder might describe warmer conditions than they experienced in their youth. During inception, every generation experiences roughly the same climate. The changes are too slow to perceive directly, but compound over centuries into transformation. Not unique, but each different termination, either one we just lived through, is the most recent and best studied. But it is not unique. The orbital machinery has been running for millions of years, pacing ice ages in 100,000-year rhythms for the past million. Each cycle ends with a termination. Let us look at some of the others. Termination V400 and 30,000 years ago, the MIS-11 interglacial marine isotope stage 11, which followed termination V, is fascinating because it is considered one of the best analogues for our current interglacial. Why? Orbital configuration. MES-11 occurred during a period of very low eccentricity. Earth's orbit was nearly circular, just as it is today. With low eccentricity, precession has minimal effect. The primary forcing comes from obliquity. This creates a different flavour of interglacial, longer lasting, with more gradual changes, less dramatic swings. MIS-11 lasted unusually long, approximately 30,000 years, compared to 10,000, 15,000 for most interglacials. It was characterized by sustained warmth without the brief cold reversals seen in some other interglacials. Why is this important for us? If natural orbital forcing were the only factor, for example, without human CO emissions, the Holocene would probably follow an MS-11-like trajectory, a long, stable interglacial lasting 20,000, 30,000 years before gradually sliding into the next glaciation. This is what Rudderman and others have proposed, that without human influence, we'd be looking at tens of thousands of years of relatively stable interglacial climate ahead. The low eccentricity configuration means the pacemaker is weak. The next glaciation would be delayed. But of course, we've added a massive perturbation CO, so this natural trajectory is no longer playing out. Termination IV 340,000 years ago, MIS9 was a weaker interglacial. Temperatures didn't get quite as warm as MIS11 or MIS FV the Eemian. Sea level didn't rise as high. The ice sheets didn't melt as completely. Why? The orbital parameters were not as strongly aligned. Obliquity was moderate. Eccentricity was present, but not at its peak. Precession was somewhat favourable, but not optimal. This demonstrates an important point: not all interglacials are created equal. The strength and duration of an interglacial depend on the specific combination of all three orbital parameters. Some alignments produce robust and long, warm interglacials MIS5e, MIS11. Others produce weaker, shorter ones MIS9, MIS7. The ice volume records show this clearly. The interglacial peaks vary in height. Some nearly eliminate northern hemisphere ice sheets, others leave significant ice remaining in Greenland and possibly Canada. Termination 3 280,000 years ago, MIS7 is another middling interglacial warmer than MIS9, but not as warm as MIS5e or 11. What's notable about MIS7 is its structure. It shows multiple warm peaks separated by brief cold intervals. It is a multi-peaked interglacial, suggesting instability. The climate achieved warm conditions, cooled briefly, rewarmed, cooled again, before finally descending into the next glaciation, MIS6. This might reflect orbital dynamics. If precession is cycling through its 23,000-year period during the interglacial, you can get multiple warm peaks as precession repeatedly brings northern summer to perihelion, separated by cooler intervals when it swings the other way. Termination 2 140,000 years ago. The Eemian, we've already discussed this one in detail. It is the warmest recent interglacial, the one most often invoked as an analogue for potential future warming. The common thread, despite their differences, all these terminations share key features: slow build-up, fast melt. Ice accumulates over 60,000, 90,000 years. It melts in 10,000, 20,000 years, triggered by orbital forcing. Each termination occurs when summer insolation at 65 degrees N rises above a threshold. The threshold is not fixed, it depends on the state of the climate system, but the orbital forcing provides the initial push, amplified by feedbacks. CO rises during deglaciations, amplifying the warming. Albedo changes, less ice, less reflection amplify further. These feedbacks transform the relatively weak orbital signal into dramatic climate change. Sea level rises. Every termination is accompanied by major sea level rise as ice sheets melt. The amount varies 6-9 meters during Eemian, more than 120 meters during termination I because LGM ice was at its thickest, but sea level rise is the signature of deglaciation. Asymmetric in speed. Warming happens faster than cooling. Terminations are abrupt in geological terms. Inceptions are gradual. The older ones go back further, beyond the reach of detailed ice core records, and you find earlier terminations stretching back through the Pleistocene. Before the mid-Pleistocene transition 1 million years ago, The cycles were faster 40 1,000-year rhythms dominated by obliquity. There were more terminations, roughly one every 41,000 years instead of every 100,000 years. These earlier cycles were smaller in amplitude. Less ice, less dramatic warming, smaller sea level changes. The climate system was responding more directly to the stronger obliquity forcing, without the complex resonance that creates 100,000-year cycles in the late Pleistocene. But the basic principle was the same: orbital forcing changes, climate responds, ice grows and melts in rhythm. The earliest clear evidence of glacial interglacial cycles extends back about 2.6 million years to the beginning of the Quaternary period. Before that, the climate was generally warmer and didn't have large ice sheets in the northern hemisphere. Antarctica had already iced over by then. So for 2.6 million years, Earth has been oscillating, growing ice, melting ice, growing again, melting again. Dozens of cycles, dozens of terminations. Each one left its mark in ocean sediments, in landforms, in the evolution of species that had to adapt to yawing climates. And humans, genus Homo, evolved entirely within this oscillating climate. We are children of the Ice Age cycles. Our brains, our flexibility, our adaptability, all forged in the crucible of repeated glacial interglacial transitions. The Holocene as interglacial 11,700 years ago, the Younger Dryas ended. Temperatures surged. The last remnants of Ice Age climate vanished. The Holocene began. We live in that interglacial right now. This is the warm pause between ice ages. By the standards of the past million years, the Holocene is a typical interglacial in many ways: warm global temperatures. Reduced ice sheets, though Greenland and Antarctica remain, high sea level, forests at high latitudes, modern fauna distributions. But it has some unusual characteristics: stability. The Holocene has been remarkably stable compared to previous interglacials or the preceding glacial period. Temperature variations over the past 11,000 years have been relatively small, a few tenths of a degree globally, maybe 1-2 degrees Celsius regionally for events like the medieval warm period or Little Ice Age. Compare this to the wild swings of Mars 3, the unstable glacial period 60,000, 30,000 years ago, when Dansgaard-Oster events caused Greenland temperatures to jump 10-15 degrees Celsius in decades, then crash back down. Or the Younger Dryas whiplash, or the multi-peaked instability of MIS 7. The Holocene is boringly stable, which is precisely what allowed agriculture to develop and civilization to flourish. You cannot farm if the climate swings wildly every few centuries. You cannot build cities if sea level is jumping meters per century. The Holocene's predictability is its gift. What's the orbital configuration now? Where are we in the cosmic dance? Eccentricity very low. Currently 0. 167, nearly circular. This is close to the minimum eccentricity Earth's orbit achieves. The difference between perihelion and aphelion is only about 3. This means precession has minimal effect on seasonal intensity. It doesn't matter much when in the orbit the seasons occur because the sun distance barely changes. Obliquity moderate and declining. Currently 23.44 degrees, right in the middle of the 22.1 degrees, 24.5 degrees range. But it is on a declining trend. Over the next 10,000 years, it will decrease toward the minimum value. This means high latitude summer insolation will gradually decline. Precession northern summer at aphelion. Currently, northern hemisphere summer occurs in July when Earth is at aphelion farthest from Sun. This is the opposite of the configuration at the peak of deglaciation 11,000 years ago, when northern summer was at perihelion. The precession wobble has shifted through half its cycle in the intervening millennia. The result summer insolation at 65 degrees N is declining. Gradually, very gradually, but the trend is downward. We've passed the insolation peak of this interglacial, which occurred around 10,000, 11,000 years ago, and are on the descending slope. When would the next ice age come? If, and this is a big, if we were not adding CO to the atmosphere, what would happen naturally? The orbital configuration suggests we are due for a slow descent toward the next glaciation. Summer insolation at 65 degrees and will continue declining for the next 20,000 years or so as obliquity decreases. But here's the crucial detail: eccentricity is very low. With nearly circular orbit, the pacemaker is weak. The 100,000-year cycle doesn't have strong forcing. Without the eccentricity modulated precession swings, there is no strong mechanism to rapidly grow ice sheets or to rapidly melt them. This makes the current situation more like MIS-11, which also occurred during low eccentricity. And MIS-11 lasted 30,000 years, much longer than typical interglacials. Several studies have calculated when the next glaciation would begin naturally. Berger and Lothar 2002 suggested the next glaciation might not begin for another 50,000 years, specifically because of the low eccentricity. Tsodakis et al. 2012, using MIS-11 and IS-19, another low eccentricity interglacial as analogues, proposed the natural Holocene duration would be about 30,000 years, placing the next glacial inception tens of thousands of years in the future. So absent human influence, we'd likely be looking at tens of millennia of continued interglacial conditions before a slow slide into the next ice age. But that is a moot point now, because we've fundamentally altered the system. The human disruption, here's what we've done. For the past 800,000 years, through 8 complete glacial interglacial cycles, atmospheric CO has oscillated between roughly 180 ppm glacial minimum and 280 ppm interglacial maximum. It has never exceeded 300 ppm until now. Current atmospheric CO is over 420 ppm and rising. We've increased it by 50 above the natural interglacial maximum, and we are adding roughly 2-3 ppm per year. This is unprecedented in the ice core record. The last time CO was this high, we have to go back to the Pliocene epoch. 3-5 million years ago, when global temperatures were 2-3 degrees Celsius warmer than preindustrial and sea level was 15-25 meters higher. What does this mean for the orbital forcing? It swamps it. The radiative forcing from adding 140 ppm of CO to the atmosphere is several watts per square meter, globally larger than the variations in summer insolation at 65 degrees and that drive glacial interglacial cycles. We've effectively overridden the orbital pacemaker. The natural trend toward cooling has been reversed. Instead of slowly sliding toward the next glaciation, we are warming rapidly. Several studies have addressed what this means. Ganopolsky et al. 2016 modelled when the next glaciation would occur under different CO scenarios. They found that even moderate CO levels, 240 ppm, below pre-industrial would be enough to skip the next glaciation opportunity. At current CO levels, 420 ppm, they calculated that the next glaciation is delayed by at least 100,000 years, possibly longer. Clark et al. 2016 concluded that we've likely entered a superinterglacial that will last well beyond the natural Holocene duration. The massive CO pulse will take tens to hundreds of thousands of years to be naturally removed from the atmosphere absent active carbon removal technologies. So we've broken the rhythm. The 100,000 year beat that has controlled climate for 1 million years. Interrupted. The next ice age. Postponed indefinitely, or perhaps prevented entirely. This is both remarkable and unsettling. We are a young species. Behaviorally modern humans have only existed for 100,000, 200,000 years, yet we've managed to alter a climate system that operates on 100,000 year timescales. The ice will not return in 20,000 or 30,000 or even 50,000 years as it naturally might have. The orbital forcing that would grow ice sheets is now overwhelmed by greenhouse forcing that prevents ice growth. We've become a geological force, an orbital scale forcing. The Anthropocene, our current epoch, is defined by this. We've changed the climate as profoundly as the Milankovitch Cycles did, but in a century rather than 100,000 years. Implications: what does this mean? For ice ages, they are on hold. Greenland and Antarctica are not growing, they are melting. Sea level is rising, not falling. The climate trajectory is toward warmth, not cold. For sea level, instead of the slow drawdown that would characterize glacial inception, we are facing the opposite ongoing rise. How much depends on how much more CO we emit and how long it stays in the atmosphere. But we are committed to multiple meters of rise over coming centuries, even if we stopped all emissions today due to thermal inertia in the ocean and ice sheet response time. For ecosystems, species adapted to interglacial conditions will persist rather than being forced to migrate or adapt to ice age cold. But the rapid rate of warming creates different challenges. Species that evolved to handle slow, gradual changes are now facing abrupt ones. For human civilization, we've built everything: cities and agriculture and infrastructure. Political boundaries during an unusually stable interglacial. We are now pushing that system into uncharted territory. The Holocene stability that enabled civilization is ending, replaced by rapid anthropogenic change. The orbital engine is still running. Earth still wobbles and tilts and traces its ellipse. The cycles continue, but their effect on climate has been overwhelmed by what we are doing to atmospheric composition. We've become part of the machinery. Another forcing in the equation. And unlike the predictable, calculable orbital variations, human behavior is far less certain. So here we are living in a rare warm interlude between ice ages at the very moment when the orbital engine would naturally be cooling us slowly back toward glaciation. But we've thrown a wrench into those ancient works, a wrench made of carbon dioxide. The rhythm that persisted for nearly 1 million years, the 100,000 year beat that grew ice sheets and melted them 8 times in succession, has met something it never encountered before: a species capable of changing the atmosphere faster than orbital mechanics can respond. The machinery still turns, the cosmic gears still mesh. But the climate they once controlled has slipped free. To understand what this rhythm meant for the beings who evolved within it for the humans and near humans who lived and adapted and died according to its invisible beat, without ever knowing the astronomy that drove it. We need to see the machinery from their perspective, not as numbers on graphs or orbital parameters in equations, but as the world that shaped them, as home, as the only reality they knew. Watch a valley. Not just any valley, a specific one carved by ancient rivers through limestone hills in what will someday be southern France. We are going to compress time. Watch 50,000 years play out like a time-lapse film. 50,000 years ago, a small band, maybe 30 people, camps near a rock shelter. It is full glacial. The valley floor is tundra low shrubs, tough grasses, permafrost beneath. Ice glints on the northern horizon, a white wall you could walk to in a week. The band hunts reindeer, following herds that migrate through predictable corridors. They know this land. Their grandparents knew it. The cold is normal. This is the world. 40,000 years ago, 10,000 years later, the same valley, but warmer now. Trees are returning birch and pine scattered across slopes that were barren tundra. The reindeer still come, but different animals to red deer or oaks. The band's descendants still here, still adapting, have new tools now. Finer blades, bone needles. Art appears carved figurines, painted ochre. The ice has retreated slightly. Summers are longer, 30,000 years ago, colder again. The trees thin, tundra reclaims ground. Reindeer dominate once more. The people adjust heavier clothing, different hunting strategies, movements timed to the herds. Some elders tell stories of when their great-grandparents hunted different game in forests, but no one living remembers forests here. The tundra is reality. 20,000 years ago, the last glacial maximum, coldest of all, ice has advanced. The valley is marginal now on the edge of habitability. The band is smaller, resources scarcer. They spend winters in the rock shelter, burning bone for fuel when wood is gone. Some years, they move south entirely, joining other bands in warmer refugia. The valley empties. 10,000 years ago, warmth returns. Rapid warmth. Within a few generations, the valley transforms. Forests explode across the landscape, oak and elm, hazel. New animals, boar and deer, aurochs in abundance, fish in swelling rivers. The descendants return from the south, or new groups move in and find a land of plenty. The ice is gone. The world is green. 5 acts, 50,000 years. The same valley cycling through tundra and forest and tundra, near abandonment, forest again. And here's the thing, no generation saw the change. Each lived their 70 years, if they were lucky, in what seemed like a stable world. Yes, elders might recall that the herds arrived a bit earlier this year than when they were young, or that a particular valley that once held game was now too cold or too warm. But these were adjustments, not transformations. The transformation happened in the space between generations, accumulating, invisible to any individual life, but inexorable across deep time. This is what it meant to live inside the orbital machine, to be shaped by forces you could never perceive, responding to rhythms you could never comprehend, adapting to changes you experienced as random, but which were, in fact, as regular as clockwork. Deep time, selection, evolution within the cycles. The genus Homo, our lineage, emerged roughly 2.8 million years ago in Africa. The Quaternary Ice Age cycles intensified 2.6 million years ago. This is not coincidence. Our evolution happened inside the Ice Age rhythm. We are, quite literally, children of the cycles. Selection across glacial and interglacial. Think about what this means from an evolutionary perspective. If you are a species evolving in a stable environment, natural selection favors specialization. Giraffes get longer necks for eating high leaves. Polar bears get white fur for hunting on ice. Cheetahs get fast for catching gazelles on open plains. Specialization works beautifully until the environment changes, at which point your specialized adaptation becomes a liability. But Homo didn't evolve in a stable environment. For 2.6 million years, our ancestors experienced repeated oscillations, glacial periods, cold and dry, sparse resources, open landscapes. Megafauna adapted to tundra and steppe, long winters, short growing seasons. Survival favored those who could hunt large game, endure cold, plan for scarcity. Interglacial periods, warm and wet, abundant resources, forests and woodlands. Different animals, temperate adapted species, longer growing seasons. Survival favored those who could exploit diverse food sources, navigate complex terrain, adapt to plenty. The environment flipped over and over every 100,000 years or 41,000 years in the earlier Pleistocene. What kind of organism survives this? Not a specialist. A specialist thrives when conditions match its niche and dies when they do not. A generalist survives. Someone flexible enough to handle both extremes. Someone who can eat meat and plants and fish, depending on what's available. Someone who can live in forests or tundra. Someone who can invent new strategies when old ones fail. Flexibility became the ultimate survival trait, and the organ that enables flexibility is the brain. Brain growth and climate variability over the past 2 million years, hominin brain size increased dramatically. Early Homo 2 million years ago had brains around 600-700 cubic centimeters, roughly twice the size of chimpanzees, but still small by our standards. Homo erectus 1.5 million years ago, 900 cc. Homo heidelbergensis 600,000 years ago, 1200 cc. Neanderthals 300,000, 40,000 years ago, 1400, 1600 cc. Modern humans, Homo sapiens, emerged 300,000 years ago, 1350, 1450 cc average. That is more than doubling in 2 million years. In evolutionary terms, that is rapid. Why? One hypothesis, supported by recent research, climate variability itself, selected for larger brains. The logic is elegant. In a stable environment, you can rely on instinct and learned behaviors that worked for your parents and will work for your children. In a variable environment, you need to solve novel problems constantly. You need memory to recall what worked last time conditions were like this. You need planning to prepare for seasonal changes. You need social cooperation because groups survive better than individuals when resources are unpredictable. You need innovation to invent new tools when old strategies fail. All of these memory and planning and cooperation, innovation require brain power. Lots of it. Studies analyzing the relationship between climate records and hominin fossil brain sizes show correlations. When you plot brain size against climate variability over the past million years, bigger brains appear during periods of high variability. The 100,000-year glacial interglacial cycles, with their dramatic swings, correlate with accelerating brain growth. Intriguingly, recent research shows that during the past 50,000 years, brains were actually larger during cold glacial periods than during warm interglacials. Humans living at the last glacial maximum had bigger brains on average than those living in the Holocene. This might seem backwards. Should not warm abundance favour big brains? But it makes sense. Cold, variable glacial climates demanded more cognitive resources tracking mobile herds across vast territories, planning for extreme seasonal shifts, solving problems with scarce materials. Warm interglacials, being more stable and resource-rich, relaxed those selection pressures slightly. Our brains, in other words, were forged in the crucible of Ice Age chaos. Behavioral flexibility, the real adaptation brain size, is only part of the story. The more important adaptation was behavioral flexibility itself. Homo species became generalists extraordinaire. Tool use, we didn't just use tools, we innovated them constantly. Each new climate shift brought new tool industries. More on that shortly. Dietary flexibility, early hominins ate whatever was available: meat when hunting was good, plants when it was not, fish near water, shellfish on coasts, even bone marrow scavenged from carnivore kills. This omnivory meant we were not dependent on any single food source. When mammoth populations crashed, we switched to reindeer. When reindeer was scarce, we trapped hares or gathered nuts. Flexibility meant survival. Social cooperation humans developed extensive social networks. We shared food, cared for injured or elderly members, taught skills across generations, formed alliances with other bands. This social complexity provided insurance against environmental variability. If your valley had a bad year, your neighbours might not. Cultural transmission, perhaps most importantly, we learned from each other. An innovation, a better way to make spear points, a technique for preserving meat, knowledge of which plants were edible could spread through a population without waiting for genetic evolution. Culture evolved faster than genes, allowing rapid adaptation to changing conditions. Dispersal and isolation cycles, the glacial-interglacial rhythm created a pump effect on human populations. During interglacials, climate is warm. Resources abundant. Populations expand. Groups spread across broader territories. Different populations encounter each other and mix, exchange genes and ideas. During glacials, climate cold, resources scarce. Populations contract into refugia pockets of relatively habitable land. Mountains, southern peninsulas, river valleys with reliable water. Groups become isolated from each other. Gene flow stops. Populations diverge genetically and culturally. Next, interglacial warmth returns. Populations expand again from refugia. Groups that were isolated for 50,000 years meet again, mix again. This cycle repeated over and over. Expand and contract and isolate, mix. Expand and contract and isolate, mix. The result, a complex mosaic of human populations across Africa and Europe and Asia, sometimes isolated, sometimes mixing, constantly adapting to local conditions while sharing the broader trajectory of encephalization and behavioral flexibility. We are not the product of steady, gradual evolution in one stable environment. We are the product of this pulsing and fragmenting and reuniting, adapting process. The orbital cycles didn't just shape our climate, they shaped us. The people living through these cycles had no idea what was happening to them. They didn't know about orbital mechanics. They didn't know Earth's tilt was changing by fractions of a degree. They couldn't have conceived of Milankovitch cycles or eccentricity or precession. But they adapted anyway, through culture, through accumulated knowledge passed from generation to generation, through stories and skills and careful observation of a world that seemed stable but was in fact slowly shifting. Oral tradition as climate archive and elder holds at most 3 or 4 generations of direct knowledge. If they lived to 70 and they learned from grandparents who lived to 70, who learned from their grandparents, that is maybe 150, 200 years of lived memory compressed into stories and teachings. That is not long enough to perceive millennial scale climate trends, not even close, but it is long enough to notice variations. The herds arrived later this year than when my grandfather was young. That valley used to have more game. Winters feel harsher than the old stories tell. These observations accumulated, passed down, embedded in oral tradition might have preserved hints of longer patterns without anyone understanding them. Imagine stories told around Ice Age hearths. Our people came from the south, from lands that are now cold. Maybe that is cultural memory of migration during a glacial advance. The sea was once land. Maybe that is memory of lower sea levels or of coastlines drowning as ice melted. There was a time before the Great Cold. Maybe that is the Eemian, 100,000 years ago, preserved in myth. We cannot know. Oral traditions do not fossilize well, but it is intriguing to consider how much climate history might have been encoded in stories we will never recover. Practical knowledge tracking the patterns. What Ice Age people definitely had was practical, observational knowledge of their immediate environment. They tracked animal migrations with precision. When did herds arrive each spring? Which valleys did they favour? Where were calving grounds? Which mountain passes did they use? This knowledge was survival. They marked seasonal changes. First snowfall, last frost. When certain plants flowered, when fish ran in rivers, when birds returned from migration. These markers helped them time hunts, predict resource availability, move camps efficiently. They knew landscapes intimately. Where water could be found in dry seasons, which rock shelters provided best protection from wind. Where flint for tools outcropped, which plants were edible and medicinal, poisonous. All this knowledge was passed down, taught deliberately to children, reinforced through practice, shared within and between groups. And here's the key: this knowledge was dynamic. It had to be, because the world was changing. If herds started arriving earlier each spring, hunters adjusted. If a particular valley became too cold for the game they relied on, they shifted territories. If a food plant became scarce, they found alternatives. Cultural knowledge evolved faster than genes could. A new tool design could spread through a population in a generation. A successful hunting strategy could be adopted immediately. This cultural flexibility knowledge as adaptation was perhaps humanity's greatest survival tool. Cultural flexibility, not tied to one-way Ice Age humans, were not locked into a single lifestyle. They couldn't afford to be. They could switch between strategies depending on what the environment offered: hunting large game, mammoth and bison, reindeer when herds were abundant, trapping smaller animals, hares, birds when large game was scarce, fishing when near rivers or coasts, gathering plants and nuts, roots when available, scavenging when necessary. They could live in caves, rock shelters, or construct temporary camps. They could follow mobile herds or settle semi-permanently near reliable resources. They could work stone and bone and antler, wood, whatever materials the landscape provided. This flexibility itself was the adaptation, not specializing in mammoth hunting or plant gathering, but being able to do both and more, depending on what the shifting climate made available. Spiritual interpretations making sense of the world. How did Ice Age people explain climate? Not with orbital mechanics, certainly, but they had frameworks spiritual and mythological, experiential for understanding their world. Perhaps they attributed changes to gods and spirits, cosmic forces. Perhaps successful hunts or harsh winters were seen as blessings or punishments from unseen powers. Perhaps shamans or elders interpreted patterns, made predictions, performed rituals to influence weather or game abundance. We see hints of this in the archaeological record, elaborate burials suggesting belief in an afterlife, cave art that might have served ritual purposes, carved figurines that could be religious icons. The specifics are lost, but the impulse to explain, to find meaning, to create narratives about why the world behaves as it does, that is deeply human. Ice Age people surely had such narratives. The interesting thing is this: the explanations didn't matter for survival. The adaptation did. You do not need to understand Milankovitch cycles to notice that reindeer herds are arriving earlier and adjust your hunting schedule accordingly. You do not need to grasp obliquity to know that some valleys are getting colder and you should move camp. Practical knowledge works even without theoretical understanding. For hundreds of thousands of years, humans adapted to climate cycles without knowing they were cycles. The machinery turned, we responded, and we survived. Archaeological signatures of climate transitions, the abstract, becomes concrete when you look at what people left behind. The archaeological record, tools and bones, living sites, art changes as climate changes. Each shift in the orbital machine left signatures in stone and ash and bone. Tool industries change with climate. European archaeology divides the late Paleolithic into distinct industries, cultural periods defined by characteristic tool types and manufacturing techniques. These are not arbitrary categories. They correlate with climate shifts. Mousterian 100 and 60,000, 40,000 years ago, associated primarily with Neanderthals, characterized by flake tools made using prepared core techniques, scrapers and points, hand axes. These tools worked beautifully for butchering large game in open landscapes, exactly the conditions of glacial Europe. The Mousterian persisted through multiple climate cycles, adapting to both glacial cold and interglacial warmth, but it reached its peak during glacial periods. Aurignation 43,000, 28,000 years ago, the arrival of anatomically modern humans in Europe brought new technology. Blade tools long, thin flakes struck from prepared cores, bone and antler implements, awls and points, needles. The innovation specialized tools for specific tasks rather than multi-purpose hand axes. This tool industry appeared during a transitional climate period as the world moved toward the last glacial maximum. The people making these tools, early Cro-Magnons, were adapting to cooling conditions, but brought innovations from Africa and the Near East that gave them advantages. Gravechin 33,000, 22,000 years ago, the height of glacial cold. This culture thrived during the approach to the last glacial maximum. Tool innovations included small, pointed blades ideal for spears used in hunting large game across open tundra. Nets evidenced by weights and knots for trapping small game. Needles for sewing tailored clothing, essential for extreme cold. Venus figurines appear during this period, small carvings of female forms, found from France to Russia, suggesting widespread cultural connections even during harsh conditions. The Gravettians were not just surviving the cold, they were thriving, adapted specifically for Ice Age life. Magdalenian 12,000 years ago, the climate is warming. Ice sheets retreating. This is the culture of deglaciation. Bone and antler tools dominate harpoons for fishing, elaborate spear throwers, eyed needles, engraved implements. The toolkit diversifies dramatically. Why? Because the environment is diversifying. As forests return and temperatures rise, resources become more varied. Fishing becomes more important, smaller game more accessible. The Magdalenian represents adaptation to abundance and change. And this is the culture that produced the greatest cave art Lascaux and Altamira. Chauvet, though Chauvet is actually Aurignacian 40,000 years old. Art flourishes during resource abundance. The pattern is clear tool technologies track climate. Cold periods favor tools for hunting megafauna across open landscapes. Warm periods bring diversification and specialization, elaboration. Each cultural industry represents an adaptive response to environmental conditions shaped by orbital forcing. Site distribution shifts. Where people lived changed with climate. During glacial periods, archaeological sites cluster in southern Refugia Spain, southern France and Italy, the Balkans, the Crimea. These are the places where ice didn't reach, where forests or steppe provided enough resources for survival. Northern Europe, Scandinavia, Britain north of the Thames. Northern Germany was either under ice or too cold and barren for sustained habitation. Sites from glacial periods are fewer overall, smaller populations. Harsher conditions meant lower carrying capacity. Living sites favor caves and rock shelters, natural protection from wind and cold. During interglacial periods, sites spread across much broader areas. People reoccupy Scandinavia and Britain, Northern Europe. Population densities increase. More sites mean more people. Open-air sites become common. Camps along rivers, on plateaus, near game migration routes. Less need for caves when climate is mild. You can literally map the retreat and advance of human populations across Europe in sync with ice sheets. As ice grows, people retreat south and compress into refugia. As ice melts, people expand north, following resources into newly opened lands. Subsistence shifts reading the bones. What people ate changed with climate. We know this from faunal assemblages, the animal bones left at archaeological sites, and from isotope analysis of human bones. Glacial periods, heavy reliance on large game. At Gravettian sites, bones of mammoth, woolly rhinoceros and reindeer and horse, and bison dominate. These are cold-adapted megafauna that thrived in tundra and mammoth steppe. Hunting focused on herding species that could be taken in large numbers during seasonal migrations. Plant material rare, poor preservation, but also genuinely less available in cold, dry climates. Isotope analysis of Neanderthal bones shows they were almost exclusively carnivorous at the top of the food chain, eating large herbivores. This makes sense in glacial Europe. Meat was the most reliable calorie source. Interglacial periods, diet diversifies. More variety of game species, red deer and boar, aurochs. Increased fishing evidence of fish bones and fishing gear increases during warm periods. Shellfish consumption increases at coastal sites. Plant foods become more important, though direct evidence is scarce due to preservation issues. We can infer from tool types designed for plant processing. Modern humans during warming periods show more dietary diversity than Neanderthals. This flexibility, eating whatever was available, may have been a survival advantage during transitions. Art and symbolism flourishing cave art, those stunning painted bison and horses and handprints, doesn't appear randomly in time. The greatest artistic flourishing occurs during specific periods late Aurignacian and especially Magdalenian, roughly 40,000, 12,000 years ago. This spans the last glacial maximum and the deglaciation period. Why then? Several factors likely contributed population aggregation. During climate transitions, groups that had been dispersed might gather in certain regions with reliable resources. Larger social gatherings create contexts for artistic expression, ritual and storytelling, social bonding through shared symbolic activities. Resource stability. The Magdalenian, despite being a glacial period, saw stable enough resource bases, especially reindeer herds, that people could afford time for non-subsistence activities. Art requires leisure time not spent desperately finding food. Cognitive capacity and culture. By 40,000 years ago, modern humans had fully developed symbolic thinking. Art is one expression of that capacity. Climate might have influenced when and where art appeared, but the capability was already there, waiting for conditions that allowed its expression. The cave art provides another window into the animals. People knew the species depicted match the climate. Aurignacian cave art shows lions and rhinoceros and mammoths, horses, cold-adapted megafauna. Later art, as climate warms, begins showing more temperate species. The art doesn't just depict the Ice Age world, it confirms it, painting pictures of the animals that lived in the orbital machine's cold phases. Two human species navigated the last glacial cycle in Europe: Neanderthals and anatomically modern humans. Both were smart, both were capable, both faced the same climate oscillations. Only one survived. Understanding why requires looking at how each species responded to the Ice Age rhythm. Neanderthal adaptation specialists of the cold Neanderthals evolved in Ice Age Europe. They'd been there for at least 350,000 years through multiple glacial interglacial cycles, including the Eemian interglacial 130,000 years ago, and the subsequent descent into the last glaciation. They were exquisitely adapted to cold. Physical adaptations: stocky, build-wide bodies, short limbs, reduced surface area, and conserved heat-classic cold climate body proportions, similar to modern Arctic peoples. Large nasal cavities warmed and humidified cold air before it reached lungs. Robust bones and powerful muscles suited for the demands of hunting large game with thrusting spears at close range. Behavioral adaptations: sophisticated stone tool technology, Mysterian industry, use of fire, construction of shelters, burial of dead. Evidence of caring for injured individuals, use of symbolic materials like ochre and shell beads in later periods. Hunting prowess: Neanderthals were formidable hunters. They took down woolly mammoth and bison and reindeer, rhinoceros megafauna of glacial Europe. Skeletal analysis shows they had injuries consistent with close quarters, hunting broken bones, healed trauma, the kind of damage you'd get wrestling large, dangerous prey. Potential vulnerabilities: smaller population networks. Neanderthal groups seem to have been more isolated from each other than modern human groups. Less gene flow, less exchange of innovations, narrower diet, heavy reliance on meat, less dietary flexibility. This worked fine when megafauna were abundant, but became problematic when resources fluctuated. Lower population density overall, fewer Neanderthals across their range than modern humans in equivalent areas. Modern human adaptation, flexible generalists, anatomically modern humans evolved in Africa around 300,000 years ago. By 100,000 years ago, they'd begun expanding out of Africa. By 45,000 years ago, they reached Europe. They brought different strategies, physical adaptations, more graceful build, lighter bones, taller, more linear body proportions, heat adapted from African origins, less specifically cold adapted than Neanderthals, but compensated with technology better, clothing tailored, sewn garments using eyed needles, behavioral flexibility diverse toolkit, including blade technology, bone tools and nets, fishing gear. Evidence of long-distance trade networks, shells, high-quality stone moved hundreds of kilometers, larger social networks connecting distant groups. Dietary diversity, modern humans ate everything. Isotope analysis shows they consumed fish and plants, small game and birds, shellfish, not just large mammals. This omnivory provided buffer against resource fluctuations. When reindeer were scarce, they shifted to other foods. Innovation, rapid cultural evolution. New tool types appear and spread quickly. Art, personal ornaments. Complex symbolic behavior explode during the Upper Paleolithic 40,000, 10,000 years ago, when modern humans dominate Europe. The overlap period 45,000, 40,000 years ago for perhaps 5,000, 10,000 years. Both species coexisted in Europe. They occupied overlapping territories. They experienced the same climate oscillations, particularly the cold state eels Dansgaard Oster events between 45,000 and 40,000 years ago that brought periods of extreme cold and aridity. Recent research using stalagmite climate records shows that these cold stadials coincided with gaps in the Neanderthal archaeological record times when Neanderthal populations crashed or disappeared from regions, followed by modern human expansion into those same areas. The hypothesis Neanderthals were more vulnerable to rapid climate variability. Each cold stadial hit Neanderthals hard. Populations declined. Some regions were abandoned. When climate warmed again, modern humans expanding from refugia, connected in larger networks, with more flexible subsistence strategies moved into territories Neanderthals had depopulated. Over repeated climate cycles, this pattern led to progressive Neanderthal decline and modern human expansion. Not necessarily through direct conflict, though that may have occurred, but through competitive exclusion. Modern humans simply outcompeted Neanderthals for resources during climate stress periods. By 40,000 years ago, Neanderthals were confined to southern refugia. By 35,000 years ago, even those populations were gone. The last known Neanderthals at sites like Gorham's Cave in Gibraltar disappeared around 40,000 and 37,000 years ago. Modern humans survived where Neanderthals didn't, not because moderns were smarter brain sizes were comparable, perhaps even larger in Neanderthals, but because flexibility beats specialization when the climate was oscillating rapidly. And then, 11,700 years ago, something remarkable happened. The climate stabilized. The younger dryas ended. Rapid warming, perhaps 10 degrees Celsius in Greenland in just 50 years, pushed global climate into the Holocene, the current interglacial. But this was not just another interglacial. This one was different. Holocene stability. For the past 11,700 years, Earth's climate has been more stable than at any time in the previous 100,000 years. Look at temperature records from ice cores. During the last glacial period 12,000 years ago, the signal is noisy wild swings on centennial to millennial timescales. Dansgaard-Oster events causing 10-15 degrees Celsius temperature jumps in decades. Heinrich events causing massive iceberg discharges and climate chaos. Then the Holocene begins. The noise quiets. Temperature variations are measured in fractions of a degree globally, maybe 1-2 degrees Celsius regionally, for events like the medieval warm period or Little Ice Age. The amplitude of variability dropped by an order of magnitude. This stability is unusual. Previous interglacials show more variability. The Eemian, for instance, had abrupt cold events interrupting the warm period. The Holocene is boring by Ice Age standards, and that is precisely what made it special. Why the stability? Partly, it is orbital configuration. Low eccentricity means weak precession effects, which means less dramatic seasonal forcing changes. The climate system has fewer external perturbations. Partly, it is internal feedbacks. The ocean circulation stabilized. The remaining ice sheets Greenland, Antarctica reached equilibrium. Vegetation expanded and stabilized. The whole climate system settled into a relatively steady state. The result for 11,700 years, you could predict with reasonable confidence that next year would be similar to this year. Next decade similar to this decade. Seasons would arrive on schedule. Rivers would flow reliably. Coastal areas would remain coastal. Predictability. Stability. The gift of the Holocene. Agriculture requires stability. Farming is a gamble. You plant seeds in spring, trusting that summer will come, that rain will fall, but not too much, that frost will not kill seedlings, that you will be able to harvest in fall. You invest months of labor into crops that haven't yielded yet. You stay in one place instead of following mobile game. You commit. This gamble only works if climate is predictable. During the wild swings of the last glacial period, farming would have been suicide. Imagine planting wheat, then having the younger, driest hit temperatures plummet, growing season shrinks by half, your entire crop fails. You starve. Your gamble killed you. Mobile foraging was safer. If one area had bad conditions, you moved. If herds migrated early, you followed. Flexibility meant survival during climate chaos. But in the Holocene, with its unprecedented stability, the calculation changed. Farming became viable and eventually almost compulsory. Agricultural origins in the Holocene, multiple independent agricultural revolutions occurred during the early to mid-Holocene Fertile Crescent Levant 11,000, 10,000 years ago. Wheat and barley and lentils, chickpeas, sheep, goats. The earliest evidence of deliberate cultivation appears almost immediately after the end of the Younger Dryas, once climate stabilized. China, 10,000, 9,000 years ago. Millet in the north, rice in the south, pigs, chickens. Mesoamerica, 9,000, 8,000 years ago. Maize, corn and beans, squash. Sub-Saharan Africa, 5,000, 4,000 years ago. Sorghum and millet, yams. New Guinea, 10,000, 9,000 years ago. Taro and banana, sugarcane, all during the Holocene, none during the preceding 100,000 years of Pleistocene climate variability, despite anatomically modern humans existing for 200,000 years and being cognitively capable of agriculture much earlier. The timing is not coincidence. Research shows that late Pleistocene climates were hostile to agriculture, highly variable on decadal to centennial timescales. Low atmospheric CO, which limits plant growth, glacial CO, was 180-190 ppm compared to pre-industrial Holocene 280 ppm, and extreme aridity in many regions. Agriculture was not just difficult, it was likely impossible, or at least far too risky to sustain. The Holocene removed those constraints. Climate stabilized. CO rose from outgassing oceans as they warmed. Growing seasons lengthened and became predictable, and agriculture independently in multiple centers emerged. From flexible foragers to settled farmers, this was a fundamental shift in human existence. For hundreds of thousands of years, Homo species were mobile, flexible foragers. We followed resources. We adapted to whatever the environment provided. We didn't control our food supply, we found it. Agriculture flipped that. We settled down. We modified the landscape to produce food. We domesticated plants and animals. We stored surpluses. We built permanent structures. Populations grew. And with agriculture came everything else: villages, then towns, then cities. Social stratification, specialization of labor, writing, states, civilization. All of this, everything that defines modern human society, became possible because of Holocene climate stability. The orbital machine, having cycled between ice and warmth for nearly 1 million years, happened to settle into a warm, stable state. And in that brief window of predictability, humans stopped moving and started building. It is worth pausing to appreciate how contingent this is. If Earth had entered another cold, variable glacial period instead of the stable Holocene, agriculture might never have developed. We might still be mobile foragers, brilliant and adaptable, but without cities or writing or complex societies. The orbital cycles shaped not just our evolution, but the very possibility of civilization. For millions of years, the orbital engine turned, indifferent to the beings below. Ice advanced and retreated. Climates swung. Species adapted or vanished. Humans, flexible and clever, cooperative, learned to dance with the machine without ever understanding the music. We evolved inside the rhythm. Our brains grew large in response to its chaos. Our flexibility became our defining trait. Our cultures adapted faster than our genes, allowing us to survive transitions that killed less adaptable species. Neanderthals thrived for 350,000 years in Ice Age Europe, specialized for the cold. But when rapid climate variability hit during their final millennia, they couldn't adapt fast enough. We more flexible, more networked, more diverse in our strategies outsurvived them. And then, 11,700 years ago, the machine gave us something: unprecedented stability. A warm, predictable interglacial that didn't oscillate wildly. And in that stable moment, we stopped moving and started farming. Everything that followed cities and states and writing and technology, the entire edifice of modern civilization rests on that foundation of Holocene climate stability. But we are no longer just passengers in the machine. We've grabbed the controls. We've added massive amounts of CO to the atmosphere, more than at any time in the past 3 million years. We've overridden the orbital forcing, delayed the next ice age and pushed climate into uncharted territory. To understand what we've changed and what it means, we need to step back and see the full sweep, all the cycles, all the transitions, all the way back to when the rhythm first began, to watch the machinery from the outside across millions of years and glimpse where the pattern leads. That is where we turn next. Millions of years, and what comes next, you are watching Earth from space. Not the blue marble of today, but Earth rewound. A time lapse moving backward through millions of years. Start now in our familiar present: white caps at the poles, Greenland covered, Antarctica buried, blue oceans, green and brown continents. Rewind. The ice shrinks slightly, then grows, then shrinks again. The rhythm, glacial cycles pulsing every 100,000 years. Ice sheets spreading across Canada and Scandinavia, then retreating, over and over. The planetary heartbeat. Keep rewinding. 1 million years ago, 2 million. The ice pulses continue, but the rhythm shifts faster now, every 41,000 years, instead of 100,000. Northern ice sheets still appear and vanish, but they are smaller, briefer. 3 million years ago, northern ice becomes sporadic. Greenland only occasionally white. Antarctica alone maintains permanent ice. 10 million, 20, 30. The Antarctic ice sheet shrinks, then stabilizes. But the northern hemisphere, almost no ice at all. Arctic Ocean ice free for much of the year. Greenland green. 34 million years ago. And here watch this moment Antarctica transforms. Small glaciers on mountain peaks suddenly spread. Within a few 100,000 years, the entire continent is encased in ice for the first time in tens of millions of years. This is when it began. Not the glacial cycles you've been watching, not the Quaternary Ice Age with its Milankovitch rhythms. Something bigger, longer. The late Cenozoic Ice Age, the epoch we still inhabit. Before this moment, Earth was a different planet. Go back 50 million years. No ice sheets anywhere. Forests grew in Antarctica. Palm trees thrived in Alaska. Crocodiles swam in Arctic rivers. Global temperatures 10-12 degrees Celsius warmer than today. Atmospheric CO over 1,000 parts per million. This was the last time Earth was truly ice-free at the poles. A greenhouse world. The planetary norm. Because here's the revelation: Ice Age Earth is the anomaly. For most of the past billion years, roughly 3/4 of that time Earth had no permanent ice sheets. Warm oceans lapped at ice-free poles. The planet's default state is warm. We live in rare frozen time. The question is, how did we get here? What turned a warm greenhouse world into an ice house? And perhaps more urgently, where do we go from here? When did the Ice Age begin? The Ice Age we are living through started 34 million years ago. But to understand why, we need to follow Earth's long cooling trend backward through deep time. The Cenozoic cooling 65 million years ago, when the asteroid struck and the dinosaurs vanished, Earth was warm. The Paleocene-Eocene thermal maximum, around 56 million years ago, marked the hottest point. Global average temperatures near 30 degrees Celsius, perhaps 15 degrees Celsius warmer than today. No ice anywhere. Even winter temperatures in polar regions stayed above freezing. Then, and slowly, Earth began cooling. 50 million years ago, still very warm, but imperceptibly less so. CO levels beginning their long decline from peak greenhouse levels of perhaps 1,500 2,000 parts per million. 40 million years ago, first hints of cooling at high southern latitudes. Small, seasonal glaciers might have formed on Antarctic mountains. 34 million years ago, the Eocene-Oligocene boundary. The moment everything changed. Within about 400,000 years, geologically instantaneous permanent ice sheets formed across East Antarctica. Deep ocean temperatures plummeted by 2-3 degrees Celsius. Benthic foraminifera oxygen isotope ratios shifted by 1.5 per mil, recording both cooling and ice growth. A greenhouse world became an isohouse world, initiating the late Cenozoic ice age that continues today. What triggered it? The great debate: mountains and volcanoes, or oceans. Research points to multiple interacting factors, and scientists continue debating their relative importance. The CO threshold hypothesis: when atmospheric CO dropped below approximately 600, 750 parts per million, conditions became favorable for Antarctic glaciation. Above that threshold, even with favorable orbital configurations, ice couldn't establish a permanent foothold. Below it, ice could grow and persist. Around 34 million years ago, Earth crossed that threshold. But what caused CO to decline? Mountain building and weathering. The uplift weathering hypothesis, proposed by Maureen Ramo and colleagues in the 1980s, suggests that mountain building, particularly the Himalayas and Tibetan Plateau, following the India-Eurasia collision, dramatically increased silicate weathering rates. Fresh rock surfaces exposed at high elevations, combined with intense monsoon rainfall, created ideal conditions for CO drawdown through chemical weathering. When CO dissolves in rainwater, it forms carbonic acid, which reacts with silicate rocks. The dissolved carbon eventually flows to the ocean, where it is sequestered in marine sediments. Recent evidence provides mixed support. Strontium isotope ratios in seawater became more radiogenic through the Cenozoic, potentially indicating increased weathering of continental rocks. But newer analyses suggest the Himalayan weathering contribution may have been overestimated. Other factors like changing ocean chemistry and biological productivity also matter. Declining volcanism, an alternative hypothesis, suggests that volcanic CO degassing simply decreased as plate tectonic activity slowed. After 52 million years ago, mid-ocean ridge spreading rates declined, reducing volcanic outgassing. The closure of the Neo-Tethys Ocean around 50 million years ago eliminated associated volcanic arcs. Less volcanic input, steady weathering output, declining atmospheric CO. A 2020 study found that the waning of volcanic arc magmatism along southern Eurasia coincided precisely with phases of atmospheric carbon reduction during the Cenozoic, suggesting reduced degassing contributed significantly to cooling. The truth? Probably both. Declining volcanism reduced CO inputs, while increased or at least sustained weathering removed CO from the atmosphere. The combination pushed CO below the ice sheet threshold. Ocean gateway, opening plate tectonics, also reconfigured ocean circulation. The opening of the Drake Passage between South America and Antarctica around 34 million years ago, and the Tasmanian Gateway between Australia and Antarctica allowed the Antarctic circumpolar current to form. This powerful ocean current isolated Antarctica thermally, cutting it off from warm equatorial waters. Surrounded by cold water, with declining CO making the atmosphere less effective at trapping heat, Antarctica cooled rapidly. The Antarctic deep frees small ice caps formed in the Gamburtsev Mountains and Transantarctic Mountains high elevation regions where temperatures dropped below freezing year-round. Snow accumulated, ice spread. By 27.9 million years ago, these ice caps merged into the East Antarctic ice sheet, a continental-scale glacier covering millions of square kilometers, and once established, ice became self-reinforcing. White ice reflects 80-90 of incoming sunlight high albedo, keeping the region cold, allowing more ice to grow, which reflects more sunlight. The feedback loop locked Antarctica into permanent glaciation. By 28 million years ago, most of Antarctica was ice-covered. By 15 million years ago, the East Antarctic ice sheet had reached approximately its current extent. It has persisted with fluctuations ever since. For the next 31 million years, Antarctica remained frozen, but the northern hemisphere, still largely ice-free. The northern freeze a recent development fast forward to 3 million years ago. The late Pliocene, Antarctica had been frozen for 31 million years, but Greenland, mostly green, with ice limited to the highest peaks in the east and south. The Arctic, seasonally ice-covered at most. Northern continents warm enough for forests to grow far into what's now tundra. Global temperatures 2-3 degrees Celsius warmer than pre-industrial, similar to projections for our near future. Then, around 2 even to 2.6 million years ago, something shifted. The Isthmus of Panama formed, connecting North and South America. This seemingly small geographic change had massive climate consequences. It closed off ocean circulation between the Pacific and Atlantic, redirecting the Gulf Stream and changing how heat was distributed around the planet. More importantly, it strengthened the thermohaline circulation, pumping moisture-laden warm water into the North Atlantic, which then evaporated and fell as snow on high northern latitudes. More snow, cooler summers thanks to continuing orbital variations, continued gradual CO decline. Conditions aligned for northern hemisphere glaciation. Ice sheets began forming on Greenland around 2.7 million years ago. At first sporadically, growing during especially cold periods, then melting. But by 2.6 million years ago, the start of the Quaternary period and the Pleistocene epoch permanent ice established itself in the north. Atmospheric CO had dropped to between 280 and 320 ppm, cold enough that disparate ice caps over Greenland connected and covered most of the island. For the first time in hundreds of millions of years, both poles were simultaneously ice-locked, a unique configuration in Earth's long history. The Quaternary Ice Age, with its dramatic glacial-interglacial cycles, its 100,000-year rhythm. Its ice sheets covering Canada and Scandinavia represents only the latest phase of a much longer cooling trend that began 34 million years ago. We are living in Act 3 of a play that started in the Eocene. The Ice Age rhythm hasn't been constant. The pattern has evolved and shifted, transformed over the past 2.6 million years. Early Pleistocene, the 41,000-year world 2.6 to 1.2 million years ago, when Northern Hemisphere glaciation first began, ice sheets appeared and vanished in lockstep with Obliquity, the 41,000-year cycle of Earth's axial tilt. The pattern was clear every 41,000 years when tilt was at its minimum 22. 1 degrees, high northern latitudes received less summer sunshine. Snow accumulated. Ice sheets grew over Scandinavia, parts of North America and northern Europe. Not massive sheets smaller, shallower than what would come later. Then, when tilt increased back toward its maximum 24.5 degrees, summer sunshine at high latitudes intensified. Ice melted relatively quickly. Glacial periods lasted roughly 30,000, 40,000 years, interglacials about 10,000 years. The 100,000-year eccentricity cycle was barely visible in climate records. Precession's 19,000, 23,000-year cycle appeared as smaller oscillations superimposed on the dominant 41,000-year beat. This made sense. Obliquity has the strongest direct effect on high-latitude summer insolation, exactly the factor that controls ice sheet growth and decay. The climate system was responding to the strongest orbital forcing. Mid-Pleistocene transition, when the rhythm changed 1.2 to 0.8 million years ago, around 1.2 million years ago, something began shifting. The 41,000-year cycles didn't disappear, but they weakened. A new rhythm emerged 100,000 years. By 700,000, 650,000 years ago, this new rhythm dominated. Glacial cycles now lasted roughly 80,000, 100,000 years, with rapid terminations into brief 10,000, 20,000 year interglacials. The familiar sawtooth pattern of the late Pleistocene had arrived. This was puzzling. Eccentricity, the 100,000-year orbital cycle, is the weakest of the three Milankovitch forcings. It changes total annual sunlight by only 0.2, far less than Obliquity's 2-3 or Precession's 4 seasonal effects. Why would the weakest cycle suddenly dominate? Scientists called this the mid-Pleistocene transition MPT, and for decades it remained one of paleoclimatology's biggest mysteries. Solving the transition, the regolith hypothesis, recent research suggests two interacting factors caused the MPT1. Gradual CO decline atmospheric. CO continued its slow decrease throughout the Pleistocene, dropping from perhaps 283 ppm in the early Pleistocene toward 200 and 6,280 ppm by the late Pleistocene. This made the climate system more sensitive to orbital forcing closer to the threshold, where small changes could trigger large responses. 2. Regolith removal. This is where it gets interesting. Before the Quaternary, northern North America and northern Eurasia were covered by thick layers of regolith weathered rock and sediment, 10-50 meters deep in places. When ice sheets first formed, they slid easily over this soft substrate. Ice with its base on deformable regolith flows quickly, which limits how thick it can grow. The faster basal sliding spreads ice outward before it can pile up. These early ice sheets were wider but thinner than later ones. Thinner ice has gentler surface slopes and larger ablation zones, making it more sensitive to summer insolation changes. Every time summer sunshine increased, the ice melted quickly. The threshold for ice sheet survival was high. But here's what happened: each glaciation scraped and eroded the regolith. Ice flowing over the substrate carried sediment away from central areas, depositing it along ice sheet margins and into the ocean. After millions of years of repeated glaciations, the regolith was gone from the core areas that ice sheets occupied Canada's Precambrian shield, Scandinavia's crystalline bedrock exposing bare, hard bedrock underneath. Osmium isotope evidence from ocean sediments shows a major change in weathering flux around 900,700,000 years ago, consistent with this transition from soft regolith to hard bedrock. Ice sheets resting on hard bedrock behave differently. Less basal sliding means ice can grow thicker and narrower. Thicker ice is more stable, less sensitive to climate fluctuations. The threshold for ice sheet survival dropped. Now ice sheets could survive through multiple smaller orbital cycles, 41 K obliquity, 1923 K precession, accumulating mass over 60,000, 80,000 years. They grew through several cycles before conditions aligned for rapid termination. The result 100,000-year glacial periods paced by eccentricity's modulation of precession, rather than direct obliquity forcing. Late Pleistocene, the 100,000-year heartbeat past 700,000 years. This is the rhythm we've focused on throughout this episode. The sawtooth pattern. 8 complete cycles in the past 800,000 years. Each cycle follows the template slow descent into glacial 60,000, 80,000 years maximum ice extent at last glacial maximum. Rapid termination 10,000, 20,000 years. Brief interglacial 10,000, 30,000 years. Repeat. Ice sheets now grew 2-3 kilometers thick over Canada and Scandinavia. During glacial maximums, they covered 45-50 million square kilometers, roughly 3 times the area of Antarctica today. Sea level dropped 100 and 2,130 meters. The 100,000-year rhythm emerged not because eccentricity directly controls climate, but because the climate system's internal dynamics, ice sheet physics, CO feedbacks, albedo effects resonated with that timescale once ice sheets became thick and stable enough to accumulate through multiple smaller cycles. The rhythm, we inherited this, is the machine into which humans were born. Homo erectus emerged during the early Pleistocene 41,000-year world. Neanderthals and modern humans evolved during the late Pleistocene 100,000-year world. The rhythm was our cradle. The variability shaped our adaptability. The transitions tested us. And the stability of the current interglacial, the Holocene, gave us the window to build civilization. What ends an ice age permanently? Not the glacial cycles those end through orbital forcing, as we've seen, but what ends an ice age entirely? What would it take to melt Antarctica, to return Earth to a greenhouse state with no permanent ice anywhere? The answer lies in the same forces that created ice ages, plate tectonics, the carbon cycle, and deep time. Continental drift, the slow shuffle Antarctica is currently positioned over the South Pole. Greenland sits at high northern latitudes. Northern continents, North America and Europe, Asia ring the Arctic Ocean. This geography is temporary. Tectonic plates move 10 centimeters per year. Over millions of years, continents drift thousands of kilometers. Antarctica has been near the South Pole for roughly 100 million years, but it will not stay there forever. Plate reconstructions suggest it will begin drifting northward over the next 50-100 million years. Once Antarctica leaves polar latitudes and moves into the Southern Ocean's mid-latitudes, ice cannot persist year-round. Summer temperatures will rise above freezing. The ice sheet, even if 3-4 kilometers thick, will melt from both surface and base. Within perhaps 10,000, 50,000 years of reaching temperate latitudes, Antarctica could be ice-free. Similarly, if Greenland drifts south, or if the configuration of northern continents changes dramatically, ocean gateways opening, land connections breaking, conditions for northern hemisphere ice sheets will disappear. Continental drift operates on timescales of tens to hundreds of millions of years. Slow, inexorable, and ultimately decisive for ice ages. The carbon thermostat weathering VS. Volcanism CO is Earth's long-term climate control. Ice ages occur when CO drops below certain thresholds, roughly 600-750 ppm for Antarctic glaciation, 280-320 ppm for full quaternary-style Northern Hemisphere glaciation. But CO levels are not static. They are controlled by an ongoing tug-of-war between sources and sink sources, CO added to atmosphere mid-ocean ridge volcanism as seafloor spreads, magma rises and releases CO subduction zone volcanism, descending plates release CO through arc volcanoes hotspot volcanism, mantle plumes, Hawaii and Iceland. Yellowstone release CO metamorphism. When carbonate rocks are heated and pressurized at depth, they release CO sink CO removed from atmosphere, silicate weathering CO dissolves in rain, reacts with rocks. Carbon buried in ocean sediments, organic carbon burial plants, and phytoplankton absorb CO. Some gets buried before decomposing carbonate formation marine organisms build shells from calcium and dissolved CO over multi-million year timescales. These processes must balance. If volcanic input exceeds weathering removal, CO rises. If weathering exceeds volcanic input, CO falls. Mountain building and the weathering sink mountain building dramatically increases weathering rates. The Himalayas and Tibetan Plateau, formed by India colliding with Eurasia over the past 50 million years, created enormous surface area of fresh rock exposed to weathering. Add in the intense monsoon rainfall, and you have a massive CO sink. For the past 50 million years, this enhanced weathering plus declining volcanism, as spreading rates slowed, has drawn CO down, contributing to Cenozoic cooling. But mountains erode. The Himalayas are currently being worn down at rates of 1 millimeter per year in some regions. Over millions of years, mountains become hills, then plains. Less exposed rock surface means less weathering, less CO removal. Meanwhile, volcanic outgassing continues at its steady background rate. Eventually 10 and 20, 50 million years from now the weathering sink will weaken while volcanic sources persist. CO will rise. When CO climbs back above ice age thresholds, probably back above 600, 1000 ppm, ice sheets can no longer persist, even at the poles. Summer temperatures at high latitudes stay above freezing. Ice melts. The natural timeline, if humans disappeared tomorrow and Earth followed its natural course. How long until the current ice age ends? Estimates cluster around 10-50 million years, depending on how quickly Antarctica drifts north, how fast the Himalayas and other mountain ranges erode, whether new mountain building episodes occur, changes in volcanic outgassing rates, evolution of ocean circulation patterns. Eventually and naturally, the current ice age will end. Earth will return to a greenhouse state, not because of anything sudden, but because the tectonic and carbon cycle conditions that enabled ice ages will gradually dissolve. Forests will return to Antarctica. The Arctic Ocean will become permanently ice-free. Global temperatures will rise 8-12 degrees Celsius above present. Sea level will be 60-70 meters higher, no Greenland or Antarctic ice sheets. This is Earth's long-term trajectory. The current ice age, 34 million years old, is a temporary deviation from the planetary norm, but eventually is tens of millions of years away. or it was. The human wrench in the works, we've changed everything. The numbers for the past 800,000 years, atmospheric CO oscillated between 180 ppm glacial periods and 280 ppm interglacials. The amplitude of variation 100 ppm never exceeded 300 ppm. Pre-industrial 1750 CE 280 ppm right at the natural interglacial level. Today 2026 over 420 ppm higher than any point in at least the past 3 million years. Rate of increase roughly 2.5 ppm per year currently, faster than at any point in the past 800,000 years, probably faster than any time in the past 50 million years. We've added roughly 1.7 trillion tons of CO, 500 gigatons of carbon to the atmosphere since the Industrial Revolution, and we are currently adding about 37 billion tons of CO, 10 gigatons of carbon per year. This is not gradual natural variation. This is geological scale forcing compressed into centuries. What this means for orbital cycles, the Milankovitch cycles continue. Earth's orbit still stretches and relaxes eccentricity. The axial tilt still oscillates between 1 degrees and 24.5 degrees obliquity. The axis still wobbles like a top precession. These cycles haven't stopped, they are hardwired into celestial mechanics. But their climatic effects are now overwhelmed by CO, natural expectation based on orbital cycles alone. Summer insolation at 65 degree SN is currently in a declining phase. Snow should eventually start accumulating in northern Canada and Scandinavia. The next glacial inception should occur in roughly 50,000 years, possibly as early as 10,000, 15,000 years in some models, or as late as 130,000 years depending on orbital configuration. But it will not happen, because CO stays in the atmosphere for tens of thousands of years. The carbon we've already emitted will keep the planet too warm for ice sheets to form for at least 50,000 years. Research by Andriy Ganopolsky and colleagues 2016 showed that even the CO already in the atmosphere, the 500 gigatons of carbon emitted to date, is enough to delay the next glaciation by 50,000 years beyond its natural timing. If we emit another 500 gigatons of carbon, which at current rates we will reach by approximately 2050-2060, the delay extends to 100,000 years or more. If total cumulative emissions reach 2,000-5,000 gigatons of carbon plausible, if we burn most remaining fossil fuels, the next glaciation might not occur for 200,000, 500,000 years. We've skipped a beat, maybe several beats in the planetary heartbeat. The 100,000-year rhythm that dominated the past million years has been suspended. The Milankovitch machine still turns, but the climate system no longer responds to its commands. The orbital engine has been overridden. An accidental geoengineering experiment. We didn't set out to cancel the next ice age. Humans burned coal and oil for energy. We cleared forests for agriculture. We built industrial civilization. For most of that time, the climate consequences were unknown. When they became known mid-20th century, they were treated as someone else's problem, some future generation's concern. But the effect is undeniable. We've ended the Quaternary glacial cycles. We've overridden Milankovitch forcing. We've become a geological force powerful enough to suppress ice ages. Some frame this as fortunate. Ice ages are harsh. Ice sheets kilometers thick covering Canada and Scandinavia would be catastrophic for modern civilization. Agricultural zones would shift. Billions of people would be displaced. Preventing that could be seen as beneficial. But this argument misses three crucial points. First, the next glaciation was not imminent. It was 10,000, 50,000 years away. Humans would have had tens of thousands of years to adapt, or more likely, to develop technology to prevent it deliberately rather than accidentally. Second, the problem is not preventing an ice age 50,000 years from now. The problem is the super interglacial we are creating right now. Third, we've lost the stability. The Holocene's climate stability, the foundation for agriculture and civilization, depended on a particular orbital configuration during a natural interglacial. We've pushed the system into a state it hasn't been in for millions of years. We do not know how stable that state will be. The immediate future, what comes next, CO at 420 ppm and rising, means we are not heading into a glacial. We are heading into warmth beyond anything the Quaternary has seen. The Pliocene as analogue, the last time Earth had CO levels around 400 ppm was the mid-Pliocene warm period, roughly 33.3 million years ago. Conditions then: global temperatures 2-3 degrees Celsius warmer than pre-industrial Arctic 10-15 degrees Celsius warmer than pre-industrial in summer sea level, 15-25 meters higher than today Greenland. Largely ice-free, only small ice caps on highest peaks, West Antarctic ice sheet, probably collapsed forests extended into Arctic regions. Permanent El Niño-like conditions in Pacific. This is where we are heading if current emissions continue. The Eemian exceeded the last interglacial, the Eemian 130,000, 115,000 years ago, peaked at roughly 1-2 degrees Celsius warmer than pre-industrial Holocene. Sea level reached 6-9 meters higher than today. Hippos in the Thames River, forests in the Sahara. We've already surpassed Eemian temperatures. Global average temperature is now approximately 1.5 degrees Celsius above pre-industrial and rising at 0.3 degrees Celsius per decade. If emissions continue on current trajectory, we will reach 2-3 degrees Celsius warming by 2100, 3-5 degrees Celsius by 2150. These are conditions not seen in the Quaternary, not in any interglacial of the past 800,000 years. Ice sheet collapse. Greenland is already losing ice at accelerating rates. Current estimates suggest complete loss of the Greenland ice sheet over 10,000 years at sustained temperatures 2 degrees Celsius above pre-industrial. That is 7 meters of sea level rise. West Antarctica shows signs of instability. The marine-based ice sheet is vulnerable to ocean warming. Collapse could contribute another 3-5 meters of sea level rise over centuries to millennia. Even parts of East Antarctica, previously considered stable, show vulnerability at sustained high temperatures. Total potential sea level rise from complete ice sheet loss. Greenland, West Antarctica, vulnerable portions of East Antarctica 10-20 meters. Not this century, not next century, but over the next millennium if warming continues. Ecosystem disruption. Climate zones are shifting poleward at roughly 5-6 kilometers per year. Many species cannot migrate that fast. Forests take centuries to establish in new regions. The rate of change exceeds evolutionary adaptation timescales. We are likely entering a mass extinction event, the sixth in Earth's history, and the first caused by a single species. The long tail of carbon, even if we stopped all emissions tomorrow, atmospheric CO would not immediately return to pre-industrial levels. Timeline for natural CO drawdown. First few decades oceans absorb about 25 of excess CO centuries oceans absorb. Another 50,000 of years weathering slowly draws down the remainder full return to pre-industrial levels 10,000, 100,000 years. The warming we've triggered will persist for thousands of years. The ice sheets we destabilize will take thousands of years to regrow, if they regrow at all. The next glaciation we've postponed will not come for 50,000, 500,000 years. Human civilization is only 10,000 years old. Agriculture only 12,000 years old. Writing only 5,000 years old. We've made decisions in the past 200 years that will echo for 100,000. The very long future, what happens after us, zoom out, way out, to timescales that make empires seem like Mayfly lives. Scenario 1, humanity disappears, imagine humans vanish tomorrow, along with all our infrastructure and industries, emissions. What happens to climate? Years 1,000 rapid initial changes. Forests regrow over cleared land. Carbon-absorbing vegetation expands. Atmospheric CO begins declining as oceans absorb excess carbon, but slowly. After 1,000 years, CO might drop from 420 ppm to perhaps 300 and 370 ppm. Still far above pre-industrial. Years 1,000, 10,000 continued slow decline. Weathering of silicate rocks draws carbon from atmosphere and buries it in ocean sediments. By 10,000 years post-human, CO perhaps 320 ppm. Approaching pre-industrial levels, but not quite there. Years 10,000, 50,000, CO gradually approaching pre-industrial 280 ppm. Orbital forcing begins mattering again. But the next natural glaciation trigger at 50,000 years arrives, when CO is still elevated, probably still too warm for ice sheet inception. Years 50,000, 100,000 CO finally reaches pre-industrial levels. Orbital cycles now control climate again, depending on exact orbital configuration. Either a glacial inception begins if insolation is low and CO is low enough, or the interglacial continues if insolation hasn't decreased enough. Models suggest the most likely outcome glaciation delayed to approximately 100,000, 130,000 years post-industrial revolution. Years 100,000 eventually, natural orbital forcing reasserts full control. Glacial interglacial cycles resume, following Milankovitch rhythms. Earth returns to its quaternary pattern for a while. Years 1050 million, regardless of human impact. The natural end of the current ice age approaches as tectonic and carbon cycle processes play out. Antarctica drifts north. Mountains erode. CO rises naturally. Ice sheets melt permanently. Earth returns to greenhouse state. Scenario 2, humanity continues. Emissions continue if we keep burning fossil fuels through this century and beyond. Years 300 CO climbs to 600, 1,000 ppm, depending on total emissions. Global temperature 3-6 degrees Celsius above pre-industrial. Greenland melts. West Antarctica collapses. Sea level 10-15 meters. Mega droughts, extreme weather, ecosystem collapse. Human civilization either adapts dramatically or fragments. Years 310,000 emissions eventually cease. Fossil fuels exhausted or society transitions away. but CO stays elevated for millennia. Climate remains in super interglacial state, warmer than any point in past 3-5 million years. Prolonged warmth thousands of years could trigger collapse of East Antarctic ice sheet margins, adding another 5-15 meters sea level rise. Years 10,000, 100,000 very slow CO drawdown through weathering. Planet eventually cools back toward interglacial baseline, but this takes tens of thousands of years. Years 100,000, 500,000 next glaciation finally possible, but timing highly uncertain. Could be delayed 200,000, 500,000 years beyond natural schedule. Years 500,000 natural processes dominate again. Human carbon pulse becomes a brief spike in geological record, visible for millions of years, but no longer controlling climate. Scenario 3 active carbon removal hypothetical future where civilization survives and deliberately removes CO years 0-500 massive deployment of carbon capture technology and reforestation, ocean fertilization, enhanced weathering spreading crushed basalt to accelerate CO drawdown. CO could potentially be drawn back to pre-industrial levels within centuries rather than millennia. Years 550,000 maintained at target levels through active management. Orbital cycles allowed to control climate naturally. Next glaciation occurs on natural schedule or is prevented deliberately if humans decide they prefer warm Earth. This scenario requires enormous energy and technology and coordination and resources. Possible. Maybe. Likely. Unknown. The sun's long shadow, all these scenarios assume the sun remains relatively constant. But it doesn't. The sun is slowly brightening, increasing luminosity by approximately 1 every 100 million years due to hydrogen fusion gradually changing the sun's core composition. 100 million years from now, sun 1 brighter. Earth's equilibrium temperature rises. Even without high SO, permanent ice sheets become difficult to maintain. 500 million years from now, sun 5 brighter. Earth's oceans begin evaporating faster than rainfall can replenish them. Runaway greenhouse effect becomes possible. Complex life struggles. 1-2 billion years from now, sun 10-20 brighter. Earth becomes uninhabitable. Oceans evaporate completely. Surface temperatures exceed 100 degrees Celsius. Life, if it exists, retreats to subsurface refugia before eventually going extinct. 5 billion years from now, sun becomes red giant and expands, possibly engulfs Earth. Game over. But these are timescales so vast that human civilization, even if it survives millions of years, will be unrecognizable. Perhaps our descendants leave Earth entirely, spreading to other worlds, leaving this planet to its slow solar death. Deep time perspective, the Ice Age that began 34 million years ago will eventually end. Even if humans hadn't interfered, it was always temporary, a brief cold phase in Earth's predominantly warm history. Humans accelerated that end. We've compressed what should have taken 10-50 million years of natural processes into mere centuries. We've become a geological force. The Anthropocene epoch, whether or not it is officially recognized, represents a real boundary in Earth's climate history. A moment when one species gained the power to override planetary scale processes that operate on timescales of millennia. And we did it accidentally. We didn't intend to cancel the next ice age. We just wanted energy and food and comfort, progress. The consequences will outlast everything we've ever built. Remember the two valleys from the beginning of this episode. The same place, same latitude, 120,000 years ago warm and forested, Eemian interglacial, hippos and elephants. 20,000 years ago ice on the northern horizon and tundra, glacial cold, mammoths and reindeer. Now you understand why orbital cycles drove that difference. Milankovitch rhythms, eccentricity and obliquity. Precession shifted summer sunlight at 65 degrees N by just a few percent. But those few percent, amplified by feedback's ice albedo and CO, vegetation, transformed the world. That pattern repeated 8 times in the past 800,000 years. Slow descent into glacial over 80,000 years. Rapid termination in 10,000, 20,000 years. Brief warm interglacial. Repeat. A planetary heartbeat ticking in 100,000-year intervals. You understand the engine, now 3 orbital dances, each on its own timescale, combining to modulate summer sunshine. Ice sheets responding slowly to those nudges, growing when summer's cool, collapsing when summer's warm. CO amplifying the signal, ocean circulation shifting, dust and vegetation and albedo all feeding back. A climate machine driven by astronomy, executed by physics, recorded in ice and mud and stone. You understand the history 34 million years ago. Antarctica froze when CO crossed a threshold. For 31 million years, the south stayed frozen while the north remained warm. Then, 2.6 million years ago, the north finally froze too. Last million years, the rhythm settled into its 100,000-year beat, not because eccentricity is strong, but because ice sheet dynamics and CO feedbacks resonate with that timescale. You understand the human story. We evolved inside this machine. Our brains grew large adapting to climate variability. Our behavioral flexibility, the defining human trait, emerged from surviving transitions between glacial and interglacial worlds. Neanderthals thrived for 350,000 years, but couldn't adapt fast enough when rapid oscillations hit. We could. And 11,700 years ago, the machine gave us a gift, the Holocene. Unprecedented climate stability, predictable seasons, reliable resources. In that stable window, we stopped moving and started building agriculture, cities, writing, technology, civilization. Everything that defines modernity rests on Holocene stability. But now we've grabbed the controls. The orbital machine still turns. Earth still wobbles and tilts and traces its ellipse through space, patient and indifferent. The cosmic clockwork continues, ticking out its rhythms in millennia, but we've muted its effects. We've overridden the natural sequence. We've delayed the next glaciation by 50,000 to 500,000 years, depending on how much carbon we ultimately emit. We've broken a rhythm that persisted for nearly 1 million years. Some might call this progress mastery over nature, liberation from ice age fate. Others might call it hubris, meddling with systems we barely understand on timescales beyond our comprehension. But intention doesn't matter. The fact remains the Milankovitch cycles, those subtle celestial mechanics that carved mountains, drowned coastlines, shaped species, tested humans for hundreds of thousands of years, no longer control Earth's climate. We do. And the decisions we make in the next few centuries about energy and emissions and technology, society will echo for longer than civilization has existed, longer than anatomically modern humans have walked the Earth, longer than Neanderthals survived, longer and perhaps than our species will last. The orbital engine will still be turning 100,000 years from now, when we are long gone, when everything we've built has crumbled to dust, when even the memory of our species has faded from the planetary record. But the carbon we've added to the atmosphere will still be there. The warmth we've triggered will still persist. The ice sheets we've prevented from forming will be an absence, a gap in the record, a missing beat in the rhythm. Future geologists, if there are any, will look at ice cores, ocean sediments, atmospheric composition preserved in ancient air bubbles, and they'll see a spike, a sudden, dramatic aberration in the quaternary pattern. They'll see the moment when one species, in the span of a few centuries, rewrote the planetary script, and they'll wonder, did they know what they were doing? Did we understand the machine we were breaking? Did we care? The answer, uncomfortable as it is, we knew enough. We understood enough. We cared enough intellectually, abstractly, but we burned the carbon anyway. Sleep now, if you can. The orbital engine keeps turning. The cosmic dance continues. Earth tilts and wobbles and stretches its path through space, indifferent to the creatures crawling across its surface, unaware of the changes we've set in motion. The ice will remember. The mud will remember. The rocks will remember. And tens of thousands of years from now, long after we are gone, the planet will still be processing what we did in the blink of geological time. The rhythm we broke, the beat we skipped, the ice age we cancelled. Two people look up at the night sky. The first stands outside a rock shelter in what will someday be called France. The year is 18,000 before present. The last glacial maximum. Ice sheets stretch across the northern horizon, though from here you cannot see them, just endless tundra, cold wind, and a sky so clear the stars seem close enough to touch. He doesn't know the names we've given those stars. Polaris means nothing to him, but he knows them, knows which ones appear when, which ones mark the seasons, which constellations wheel overhead as the year turns. He has watched them his entire life, 43 winters, which makes him old. The stars do not move, not in any way he can perceive. They are eternal and fixed, the only constant in a world of harshness and scarcity. He doesn't know that Earth is tilted on its axis, that the tilt is slowly changing, that this change is why his ancestors' ancestors spoke of warmer times that he has never seen. He doesn't know about eccentricity or precession or orbital mechanics. He doesn't know he is living through the coldest phase of a 100,000-year cycle, that the ice will retreat in his great-great-grandchildren's time, that the world will warm. He just knows cold, always cold. The ice to the north feels permanent, eternal. The world has always been this way. The world will always be this way. He is wrong, of course, but he'll never know it. The second person looks up at the same patch of sky, the same stars, barely shifted in their positions despite 20,000 years passing. The year is 2026, February, a clear night in the same valley, though it is called something else now, and the landscape is unrecognizable. Forests where there was tundra, cities where there were campsites, 7 billion people where there were thousands. She knows the stars' names: Polaris, Vega, Deneb. She knows Polaris was not always the North Star, that Precession will make it Vega's turn again in 12,000 years. She knows Earth orbits the Sun in an ellipse, that the ellipse stretches and relaxes over 100,000 years, that the planet's tilt oscillates between 22.1 degrees and 24.5 degrees every 41,000 years. She knows about Milankovitch cycles. She knows that orbital mechanics drove ice ages for the past million years. She knows the ice should return, and eventually, tens of thousands of years from now. She knows her species has cancelled that return, that the carbon dioxide her civilization has added to the atmosphere has overridden orbital forcing, delayed the next glaciation by 50,000 to 500,000 years, broken a rhythm that persisted for nearly 1 million years. She knows all of this, and yet, standing under the same stars that Ice Age humans saw, she feels the same smallness, the same sense of vast forces beyond comprehension, the same humbling recognition that the universe doesn't care about her understanding. The difference is she knows the machine. She knows how it works. She knows her species has become part of it, a new gear in an ancient mechanism. She knows, and that knowledge changes nothing about the stars above, the orbital mechanics, the celestial clockwork ticking in millennia. The dance continues, whether we understand it or not. But now we've stepped onto the dance floor. What the cycles taught us, if you've stayed with us through this episode, through orbital mechanics and ice core data and ocean sediments, and the mathematical machinery of climate, you've learned something fundamental about Earth climate is not static. For most of human existence, we assumed climate was fixed, that the weather changed with seasons, but the underlying climate was permanent. We were wrong. Climate shifts on every timescale, decades and centuries and millennia, tens of millennia. The Holocene stability, the foundation for agriculture and civilization, is not normal. It is a rare gift, a temporary calm in a system that has oscillated wildly for millions of years. Small changes have enormous consequences. Earth's orbit changes by tiny fractions. Eccentricity varies by only 0.5. Tilt changes by 2.4 degrees. These are subtle shifts, you'd never notice them in a human lifetime. But amplified through feedbacks, ice albedo and CO and vegetation. Ocean circulation, they transform the planet. 3-kilometer thick ice sheets grow and melt. Sea level drops 120 meters and rises again. Entire ecosystems migrate or vanish. The lesson in complex systems with feedbacks, small inputs do not guarantee small outputs. Thresholds matter. Tipping points are real. Once you push a system past a critical point, it can reorganize into an entirely different state. Timing is everything. Orbital cycles have operated for billions of years, but they only produced dramatic ice age cycles in the past 6 million years, and only the 100,000-year rhythm in the past million years. Why? Because other conditions had to align continents at high latitudes, CO below threshold levels, ocean circulation configured just right, ice sheets on the right substrate. Remove any one factor and the pattern changes. The cycles themselves are deterministic and predictable, calculable, but their effects on climate depend entirely on the state of the Earth system they are acting upon. The orbital engine provides the pacing, but the climate system determines how or whether it responds. Stability is precious and rare. The Holocene has been stable for 11,700 years. Temperature variations of only 1-2 degrees Celsius globally, predictable seasonal patterns, reliable monsoons, steady sea level. This stability allowed agriculture, permanent settlements, surplus food production, specialization of labor and writing and states, technology, everything that makes civilization possible. But look at the full quaternary record, and you see stability is the exception. Rapid climate swings on decadal to centennial timescales. Dansgaard Oster events causing 10-15 degrees Celsius temperature jumps in Greenland within decades. Heinrich events dumping icebergs into the North Atlantic and disrupting global circulation. The Ice Age world was chaos compared to the Holocene. We evolved to handle that chaos, behavioral flexibility and adaptability, innovation. But civilization requires stability. We built everything on the assumption that climate would remain within the Holocene envelope. That assumption is no longer valid. We are part of the system. For hundreds of thousands of years, humans lived inside the climate machine without affecting it. We were passengers, shaped by the cycles but unable to influence them. No longer. We've become a geological force. We've altered atmospheric composition on a scale comparable to the difference between glacial and interglacial periods, except we did it in 2 centuries instead of tens of thousands of years. We've overridden orbital forcing. We've postponed the next ice age. We are no longer separate from the climate system. We are embedded within it. Our actions are now part of the equation, part of the mechanism, part of the dance. The privilege and the burden of understanding is knowing this. Knowing we've changed the game, knowing the consequences will outlast everything we've ever built. The privilege of understanding. In the 1920s, a Serbian mathematician named Milutin Milankovitch sat in his study running calculations. He had no ice cores, no ocean sediment records, no satellites measuring Earth's orbit with precision, no supercomputers to model climate. He had mathematics, astronomical data, and extraordinary insight, and he figured it out. He calculated how Earth's orbital variations would affect solar radiation at different latitudes. He worked out which combinations of eccentricity and obliquity and precession would cool high northern latitudes enough for ice sheets to grow. He predicted that these orbital cycles paced ice ages. For decades, his theory was largely ignored or dismissed. How could such subtle astronomical changes drive something as massive as continental ice sheets? Then, in the 1970s, the evidence arrived. Ocean sediment cores showing the pattern of ice ages going back hundreds of thousands of years. The cycles matched Milankovitch's predictions. Spectral analysis revealed dominant periodicities at 100,000 years, 41,000 years, and 23,000 years, exactly the orbital cycles he'd calculated. Vindication. One of the great triumphs of theory and observation in the history of science. Milankovitch never saw it. He died in 1958, before the confirming evidence emerged. But he understood. Through pure thought and calculation and insight, he grasped the machinery of ice ages. We are the first generation of humans to fully understand this machinery. Ice Age peoples lived through glacial interglacial transitions without knowing why. They adapted brilliantly following resources, innovating technologies, surviving climate swings that would break less flexible species, but they didn't understand the underlying cause. Even a century ago, we didn't truly understand. We knew ice ages had occurred, but the mechanisms remained mysterious. Now we know. We know the orbital cycles. We know how they modulate insulation. We know how ice sheets respond. We know the feedback's albedo and CO and dust vegetation. We know the timescales. We know the mid-Pleistocene transition. We know why the 100,000-year rhythm emerged. We can look at ice core records and ocean sediment cores and read the climate history of the past 800,000 years, decoded in oxygen isotopes and dust layers and trapped air bubbles. We can calculate past and future orbital configurations and predict their climatic effects. We understand the machine our ancestors lived inside for hundreds of thousands of years without comprehending. That understanding is a privilege, a gift of science, of accumulated knowledge, of the Enlightenment tradition of observation and reason. But it is also a responsibility, because we do not just understand the machine anymore. We've changed it. We know the rhythm we've broken. We know the consequences of what we are doing, and we are doing it anyway. That is the uncomfortable truth at the heart of this episode. We have the knowledge. We understand the system. We can see what we are changing and what it means. And still, the carbon burns. The rhythm beneath everything. This is episode 3 in a much longer story. Episodes 1 and 2 showed you the ice at its maximum, what it was like, how it worked, what it did to the planet. The Ice Age world in all its harsh, frozen glory. This episode revealed why the ice came and went, why the cycles exist, why they changed over time, the invisible machinery of orbital mechanics driving the visible machinery of ice and climate. Episodes 4 and 5 coming next will narrow the focus. They'll take you to specific moments of transition. The Beeling-Aller dewarming, 14,700 years ago, when temperatures in Greenland jumped 10 degrees Celsius in perhaps 50 years. The Younger Dryas cold snap, 12,900 years ago, when the warming stopped and reversed, sending climate back into near glacial cold for more than 1,000 years. These are not abstractions. These are real events, as dramatic as anything in Earth's history, happening on timescales humans could perceive. Climate shifts within a single generation. Ice sheets collapsing in centuries. The world transforming fast enough that an elder could tell their grandchildren, I remember, when it was different. Then episodes 6 through 12 will show you the consequences. The drowned lands. Doggerland, the plain that once connected Britain to continental Europe, now submerged beneath the North Sea. Sunderland, the exposed shelf that connected Southeast Asian islands during glacial periods, now drowned. Beringia, the land bridge that enabled human migration to the Americas. All of these lands drowned because the ice melted. Because orbital mechanics shifted, because the Milankovitch cycles entered a termination phase and rapid deglaciation followed. Everything is connected. The orbital cycles drove the ice stored water. The ice melted, the seas rose. The lands drowned. This episode 3, is the hinge, the explanation, the why beneath everything else. Understanding the Milankovitch cycles means understanding why the Ice Age world existed, why it ended, why it will or will not return. It means understanding the rhythm beneath the rhythm, the deep pattern underlying all the other stories. And now, having seen that pattern, you can never unsee it. When you read about the Holocene, you will know this stability is unusual, precious, temporary. When you read about rapid climate changes, Younger Dryas and Beeling-Aller D, Dansgaard Oster events, you will know these are not random chaos. They are the system responding to forcing, crossing thresholds, reorganizing. When you read about sea level rise and drowned coastlines, you will know this happened before, many times driven by orbital mechanics and ice sheet collapse. And when you read about current climate change, the warming, the ice loss, the disruption, you will know we've hijacked the system. We've become a forcing factor comparable to orbital mechanics. We've rewritten the script. The rhythm continues, but we've changed the tempo. Permission to rest if you are still awake and listening, thinking it is okay to stop now. The cycles are slow, slower than empires, slower than civilizations, slower than written language has existed, slower than anatomically modern humans have walked the earth. The orbital engine will still be turning when you wake. Earth will still be wobbling on its axis, still tilting between 1 degrees and 24.5 degrees, still tracing its elliptical path around the sun. Eccentricity will still be oscillating, though it will take 100,000 years to complete one full cycle. You will be long gone by then. Your children and grandchildren, great-grandchildren 10,000 generations removed will be long gone by then. But the cycle will continue. Obliquity will still be changing, though so slowly you'd need a millennium to measure it. The tilt that creates our seasons, that determines how much summer sunshine reaches high latitudes, that helped pace the ice ages, it keeps changing, indifferent to whether anyone is watching. Precession will still be wobbling, like a top spinning through the cosmos. In 13,000 years, the North Star will not be Polaris anymore. It will be Vega. The axis will have wobbled to point somewhere new. But you will not be here to see it. The ice remembers, though. Locked in Antarctic cores, in Greenland ice, trapped air bubbles preserve the atmosphere from 800,000 years ago. The memory outlasts civilizations. The mud remembers. Ocean sediments accumulating millimeter by millimeter, recording the oxygen isotopes that tell us when ice grew and when it melted. The pattern is written there in forum shells, in dust layers, in the chemical signatures of ancient seawater. The rocks remember, moraines and erratics, scratches on bedrock, valleys carved by glaciers that no longer exist. The landscape itself is a record of ice that came and went according to orbital rhythms we've only recently learned to read. So rest. The story doesn't need you to stay awake. The cycles will continue. The machine will keep turning. The dance will go on. And tomorrow, or next week, or whenever you are ready, there are more stories to tell. Stories of rapid change, of worlds transforming within human lifetimes. Stories of lands drowning as seas rose, of peoples migrating as coastlines shifted. Stories of ice and water, stone and star, the deep rhythms of a planet that was here long before us and will remain long after we are gone. But for now, sleep. The orbital engine doesn't need your attention. It is patient. It is eternal. And it will be here when you return. Somewhere above you, invisible and indifferent, the cosmic clockwork turns. Earth wobbles on its axis, tilts through its slow cycle, traces its ellipse through space. The same mechanics that have operated for billions of years. The same forces that will operate for billions more. For 1,000,000 years, those tiny celestial motions pulsed ice across continents and pulled it back again. Slow accumulation, rapid collapse over and over. The rhythm carved mountains, sculpted valleys, drowned coastlines, shaped ecosystems, tested species. Humans evolved inside that rhythm. Our brains grew large, adapting to its variability. Our cultures developed flexibility to survive its transitions. Our species emerged from the machinery itself, a product of the Ice Age cycles, moulded by their relentless pressure. Then, 11,700 years ago, the rhythm gave us a gift: stability, the Holocene, and in that stable moment, we stopped migrating and started building. We created agriculture and cities and writing and technology, civilization. Everything we are, everything we've built, rests on that foundation of Holocene climate stability, itself a product of orbital mechanics, temporarily aligned just right. Now we've learned to read the clock. We've decoded the machinery. We've calculated the cycles going forward for hundreds of thousands of years. And in learning, we've changed what the clock controls. The carbon we've burned, the atmosphere we've altered, the ice sheets we've destabilized, all of it adds up to a new forcing, a human forcing, powerful enough to override orbital mechanics for the next 50,000 to 500,000 years. We've become part of the machinery. Another gear in the system, turning at our own rate, disrupting the ancient rhythm. The Milankovitch cycles will keep operating. The cosmic dance continues, but Earth no longer responds to their command. Not for a very long time. Sleep now. The ice will remember what we've done, even when we are gone. The cycles will continue their slow turning, patient and eternal. And someday, tens of thousands of years from now, when our cities are dust and our names forgotten, the orbital engine might reassert control, the rhythm might resume, the ice might return, or perhaps not. Perhaps we've changed the game so fundamentally that the old patterns can never fully restore. Only time will tell. And time, on the scale of Milankovitch cycles, is something we have in abundance, even if we are not around to see it.